Okay, good morning. It is 9 o'clock, so we'll get started. I wanted to welcome you to the second day of the ICRP Symposium. This is session 6 on the environment, where we'll hear presentations about the evolution of RAPs and DCRLs, ecosystem services, and practical applications. My name is Jason Harris. I'm from ICRP Committee 4 and Purdue University in the United States. I'd also like to introduce my co-chair, Marie-Simone Cournot, also from ICRP Committee 4 and ASNR in France. We'll begin with our rapporteur summary from Aisha Shouk from FANR here in the UAE. So Aisha, please, a summary. Thank you.
Thank you, Jason. Good morning, everyone. Today, I'm pleased to present a summary of the contributed poster and pre-recorded video. This year, we received 4 accepted abstracts, 3 posters, and 1 pre-recorded video from China, Sweden, Japan, and Sri Lanka. The first poster is by Shengxuan Wang from China. It's titled, Impacts of Legacy Site on Farmland Ecosystem, Transfer Differences of Radionuclides in Crop Organs and Ecological Risk Assessments. The study evaluates the impacts of uranium mining site on rice ecosystem by quantifying the uranium-238 transfer through soil, irrigation water, and rice plants. The results showed that uranium-238 in soil were up to 17 times higher, and in the river water near the mining site were up to 100 times higher compared to the national averages. There are 2 modeling approaches were used, static model and dynamic model. The second poster is by Caroline Stark from Sweden. It's titled, Implementing International Recommendations in Environmental Protection and Regulations, a Swedish Perspective. The aim of the study is to implement international recommendations in environmental protection within an update of Swedish regulations. The legal framework is based on the Environmental Code and Radiation Protection Act. The current rules include environmental protection but lack clear methods or quantitative levels. The study proposed that the assessment must calculate dose rate to reference animals, plant, and representative organisms using ICRP and IAA methods. The third poster is by Donova Anderson from Japan. It's titled, Long-Term Impacts of Forest Decontamination and Ambient Dose Rates and Ecosystem Dynamics in Fukushima. Over the period 2013 to 2020, the study compared remediated and non-remediated forests of different types, cedar, red pine, and broadleaf. The results showed that the broadleaf has the largest and the most sustained reduction in dose rates after decontamination, while the cedar forest showed immediate increased after decontamination due to the suspension of radionuclides. The study concluded that the long-term monitoring is necessary for balancing radiological protection and ecosystem integrity. Finally, the pre-recorded video by Swinka Wrekedu from Sri Lanka is titled Determination of Soil Redistribution Rates Using Cesium-137 Full-Out Radionuclide in Central Highlands in Sri Lanka. The aim of the study is to assess the soil erosion status of selected tea state, where tea is often grown in slopy lands. They use Cesium-137 full-out radionuclides as a tracer to study the soil movement. The results showed that the Cesium-137 concentration decreased exponentially with the soil depth, and nearly 90% of the sites show severe erosion. The study concluded that there is a need for improved soil conservation practices under climate stress. Thank you.
Thank you very much, Ayesha, for this session. And we now invite you to go and see these posters during the breaks and to interact with the authors who are present. I now invite Andy Mayal to talk us about evolving radiological protection of the environment in the ICRP system. Andy is a member of ICRP Committee 4 and co-chair of Task Group 105. He has worked at the Environment Agency in UK over 25 years, and he is Deputy Director for Nuclear Regulation Strategy at this Environment Agency. So Andy, the floor is yours.
Thank you, Marie. Good morning, everybody. Pleased to see you all here. So I've been introduced. So first thing I'm going to say is that I'm speaking on behalf of a wide range of people, a list of some of them on the screen there that have contributed to evolving the ICRP's environmental radiological protection approach, and the list is there. So I pay tribute to all those people on the slide there. I'm not going to read them all out. It'll take quite a while. So the other thing to say is I'm going to talk mainly from the perspective of Task Group 105, which is the group that I co-chair with David Copplestone. But this presentation also covers the work that Task Group 99 has done on the RAPs and DCRLs, which you've already heard about a bit. So next slide, please. Oh, I'm doing my own, aren't I? Sorry. I've got work to do. Okay, so just for this session, one of the things, these are the things I'm going to sort of focus on. I'll give you a bit of a history, a short history of the evolution of environmental radiological protection and how the several task groups are tackling this issue. Also touch a little bit on what we mean by environment in the context of ICRP's work. Its broad nature and its relationship to sustainable development, which we heard quite a bit about yesterday. Then, as I say, I'll summarise the work of Task Group 105, but also refer quite heavily to Task Group 99's work, which is further ahead than ours, and TG 125, which is looking at the concept of ecosystem services and whether that can be a tool that we can use in our framework. And then I'll talk about the next steps and summarise the findings. So just a quick potted history. I'm sure many of you will have seen this before, but the ICRP has evolved its approach to how it protects, or how its recommendations relate to the environment. Some of you will recall that in the old days, the ICRP's position was that if humans are adequately protected, then we could assume that all other parts of the ecosystem are also sufficiently protected. So that was the position up to 1990, in fact. And then it was reviewed in 1990, and pretty much that position remained more or less the same. But then there was a bit of a sea change in 2007 with the last set of recommendations, publication 103 in 2007, because at that point in time, across the world, actually in various countries, it was already being recognised that original assumption was not really valid anymore. For example, in the UK, we'd started doing assessments of the radiological impact on non-human species in the late 1990s, actually, and then in various other countries as well. So ICRP in 2007 came up with the objective for environmental protection, which is on the right-hand side there. So it's quite a long objective, but it's really focused at protecting populations of organisms rather than individual organisms. So it's about maintaining biological diversity, it's about conserving species, the health and status of natural habitats, communities and ecosystems. So that's the current objective of the framework. So what do we mean by environment? It's a good question, isn't it? It can mean a lot of things, actually. if you look at the Oxford English Dictionary definition of environment, that one at the top of the slide there, it's actually quite broad, of course, and it relates to much more than the natural environment. I'm not going to read it out for you there, but it relates in part to the external conditions of life, its existence or properties of an organism or object. So it's quite broad. So therefore, it could include things like conservation of natural resources, and that's where the ecosystem services concept is particularly useful. Maintenance of biodiversity, economic impact. Obviously, environmental impact has a potential to have an economic impact. When, for example, if seafood markets are affected by pollution, that can have an economic impact. And recreational cultural value. I would suggest that no one really wants to swim in a radioactively contaminated sea, perhaps. And indeed, the IAEA has actually produced a very useful definition of protection of the environment there on the bottom, which you can read. And it also is very broad, so it refers to environmental goods and services, so the value that humans get from using the environment, and resources, amenities, being able to enjoy the environment in a pristine state, perhaps, or near pristine, and then all the spiritual, cultural, and recreational value you get from the environment. So it's a very broad definition. So just want to keep that in mind, really, because that's what we are keeping in mind when in ICRP when we develop the system. Environment in the context of sustainable development. We heard a bit about this yesterday. I think if you're in session 4, sustainable development's often thought about in the context of environment, but actually it's a lot more than that. It also includes socio-economic development as well, and how social environment and economy work together to produce that sweet spot of sustainable development in the center of the Venn diagram, if you like. So here's just an illustration, really, of how this is just a simple mapping of some of the sustainable development goals against environmental protection. And 3 of them jump out immediately, and there will be others, actually, but the 3 that are perhaps the most relevant, perhaps, are, promoting well-being, good health and well-being, SDG 3. And then you've got SDG 14 and 15, life on land, life in water, and life on land. So you can see there, those are the kind of the immediately obvious links, but there are others, of course. And on the bottom left there, we've got the primary aim of the system of radiological protection, which talks about an appropriate level of protection, keyword there, appropriate, without unduly affecting the activities that lead to that exposure. So that's the primary aim, and you'll know that some of you have sort of seen the poster on the sustainable development out there. We are considering whether that primary aim is actually, it needs revision, perhaps, to make it more proactive, more kind of positive in its relationship to sustainable development. But we can all debate that in the years to come. Okay, so that's a bit of background, really. So considering the environment when applying the system of radiological protection, Task Group 99, which has been focusing on developing the reference animal and plant concept and the DCRLs, the derived concentration reference levels, has consulted on their report in this summer. So some of you might be aware of that, that draft report is now ready. So we have an evolution of that, which I'll talk about in a minute. But the origins of all this work really kind of lie in the paper from ICRP Main Commission, which launched the current review and revision of the system back in 2021, when that phrase there in the middle in italics in that paper recognised that there's perhaps more we should consider when we consider the environment and its protection. So it's pointing out, you know, the sustainable development agenda and so on. So, so that kind of provides a bit of a backdrop for the work of the different task groups which are working on environment. Okay, so just a brief reminder then of what is this reference animal and plant approach. It's set out in publication 108, which dates back to 2008. It's really an attempt to kind of replicate in a way the previous reference human approach that had been around for some time before that. So it's an attempt to kind of replicate that. So the idea is we have 12 referenced animals and plants, which are defined at the family level. So biologists amongst you will know we have taxonomic levels of classification of organisms. And you'll see there on the list, you know, the family level is about halfway through that taxonomic hierarchy. So the groups are on the right-hand side in the graph there. So you've got various kind of reference animals and plants representing insects and mammals and fish and so on. So the DCRLs themselves, they're grouped into three sets, like you can see on the graphic on the right-hand side. So there's 3 sets of DCRLs. The most restrictive or conservative set ranges from about 4 micrograys per hour up to 40 micrograys per hour, so it's an order of magnitude band. And then the next one is an order of magnitude higher again, and the least sensitive, another order of magnitude higher. So what do they represent? Well, they represent ranges of dose rate, absorbed dose rate, where some deleterious effects may be expected. Yeah. Okay, pressing the button, but nothing's happening. Okay, there we go. Okay, so I mentioned the consultation in this summer just gone. This was an attempt, this sets out how we are broadening that RAP approach. So when that RAP approach was published in 2008, it was recognized that it's an evolving field. It's quite a new area of work and research and so on. So it was recognized that things would change, would evolve as more scientific data came in. So the task group 99 was tasked with looking at that updated data set globally and seeing what needed to be done to enhance that approach, and that's what it did. So they, in a nutshell, what they did was to complement or supplement that existing approach with some additional criteria and benchmarks, including to use higher levels of taxonomic classification. So the approach now allows for use of groupings at the phylum or class level. So that's, biologists amongst you, that's higher than the family level. So that allows sort of a greater use of the data set, and also more flexibility in the way that you apply the criteria, so you can choose the most appropriate values. How that was done, it was done by pooling comparable effects data from across the global research results. So moving on, so what does this table show? It's actually a table from the recent report. In a nutshell, there it shows that most of the values, if you apply the new higher level DCRLs at the higher taxonomic class, most of the numbers have actually gone up. So they are less conservative, except for 2 areas where you perhaps will notice that for crustaceans, that's the line which has crab on it, and then earthworm, those two lines in the middle, they were the only two examples of where the numbers got more restrictive, so they came down.
2 minutes.
Okay. So practical application is TG105's job. So what we're looking now is how do we take those criteria and apply them in practical terms. And we're looking at a range of case studies to do that. And that work is still ongoing. So, you know, we're hoping to develop a draft report for consultation later next year. That's the learning from the case studies. That's quite broad set of learning, which we will develop further next year when we publish the draft report. But I encourage you to look at the poster for TG105, which should be out there somewhere. So we're developing a lot of learning from the different case studies. Just a quick word on application of DCRLs. In chronic exposure situations, so that's your planned exposure or existing exposure situations, for planned exposure, we recommend the lower levels of DCRLs as a criteria. For existing exposure situations, then the band of DCRLs should be kind of viewed as a kind of an ideal sort of area in which to optimize. And for acute exposure, particularly in the acute exposure in the early stage of an emergency, then it's suggested that some of the data from TG99's report can be used to kind of explain any sort of very, very significant ecosystem effects in the long term. Okay, I'm going to move swiftly on to the TG105 report now. So these are the sort of things that we're going to be focusing on in TG105 when we develop the report. So it'll include the role of environmental protection in sustainable development and making sure that the system does more good than harm. We'll look across all exposure situations, and what we'll also do actually is look at the 3 principles of radiological protection, because one thing this report will be doing is not only considering the environment as an object of protection, but also how the environment is used in decision making, such as in optimization or justification. We'll demonstrate how the DCRLs will be applied. We'll kind of emphasize the multi-criteria nature of environmental protection as well. And we will look to explain and look at how monitoring data can be used in assessments as well. So that's it. Thank you very much.
Thank you. Maybe time for one quick question. We don't see very well the room, but there is one there.
Thank you very much for your presentation. I think I have not understood one of your last slides. I thought you said that for most of the groups, the values for the DCRL went up. And then you said for planned exposure situations, you are recommending that the values should be more stringent. I have understood correctly? Or is there a contradiction in this? Why should we be more conservative with planned exposure situation if the science is telling us, yeah, the environment can also tolerate higher values?
It's working now.
Oh, yeah. Yeah, thanks for the question. Yeah, so the first table, as you say, it showed that, it indicated that for two of the groups of organisms, crustacea and annelids, worms, the values have become more restrictive. That's true. So that's that's the kind of the headlines, if you like, from the work to broaden the RAP categories and so on. So that's true. So that's the situation there. But then when the separate issue is then, as you say, is how should the DCRLs be applied in practice? And there we're not recommending any change actually, because in the current approach, the general approach has been to to use for planned exposure situations as a conservative measure to start by looking at the lower end of the DCRL bands for each of the taxonomic groupings. So that recommendation or suggestion has stayed the same. So what we're doing is, in terms of the application of the methodology, we're not recommending any change in which sort of part of the DCL bands you use. But actually, also, users can actually decide to use any part of those DCRL bands if they so wish. It's just that in that sort of planned exposure situation, as a starting point, you can look at the bottom end of that range. And quite often what we see in practice is that the exposure levels that we normally see almost entirely from the studies that we've seen, exposure rates are a lot lower in practice actually than the lower band, the lower part of the band. So in practice, planned exposure situations have not been shown to be an issue. It's primarily in the area of existing exposures where we're seeing, the potential for exposures that do exceed that lower part of the band. And that's where we're kind of suggesting that in those cases, then the band should be taken as a region to try and aim for optimizing exposures in existing exposure situations. Does that answer your question? If not, please see me afterwards and we can have a chat.
Okay, thank you, Andy. Okay, our next presentation will be given by Analia Canova. Analia is a senior radiological specialist in the Nuclear Regulatory Authority of Argentina with 30 years of experience. Her areas of expertise are in radon and norm, radiochemical measurements, and radiological and environment impact assessment. Analia is also a member of ICRP Committee 4 since 2013. So Analia, the floor is yours.
Okay, thank you very much, and good morning to everybody. Thank you for attending this session. So first of all, I want to thank to Nicole Martinez and Sarah Donaher for providing the slides. Thank you so much. Sarah is also members of the TG. So the idea is to tell you what we are doing in TG 125 regarding ecosystem services approach, and also try to share with you an examples of how these Bs can show you how we can put into practice this ecosystem services approach. So to start, maybe many of you are aware of this, but what are ecosystem services? Maybe it's an important document, the Millennium Ecosystem Assessment for 2005, and it's the definition of the benefits that humans will receive from nature. And it is divided in 4 big groups. As you can see, the provisioning groups that are the more tangible, the more things that provide nature, for example, food, drinking water, different resources. Then you have cultural services, that how we relation with nature about the enjoyment, the creativity, spiritual with the environment. Then we have regulating services, that are the services that moderate the natural processes. For example, one important is pollination that we will see from the bees, but also the control of erosion, decomposition. And then we have supporting services that, as the term says, they support all the other 3 services. For example, photosynthesis, carbon cycle, water cycle. So this is the groups to give you an idea what are we talking about from ecosystem services. It's not working. I don't know. I have to point to any place It is the big one, no? Now, okay. Sorry. Well, these two couple of slides is to show to you what ecosystem services are not. And it is very important to clarify because many of us, for example, I worked many years in radiological environmental monitoring assessment, and one of the questions we discussed in the group is, but this is the same? What are we mean by an ecosystem services approach if we've done a lot about environmental monitoring? And it's not identical, but if you see from the definitions, from the provisioning, of course, many activity concentrations of values that you have on environmental matrices will help and contribute for the ecosystem services approach. But the ecosystem services approach is much more. You bear in mind the services, the grouping of services I showed you in the first slide. And another thing that we always we thought and discussed in ICRP, we can provide a unique value to say this is a threshold, for example, for activity concentration or something to say, okay, below this value, you will not have an impaired degradation of a services or above. It is possible. It is not possible this because imagine how complex are the processes regarding the natural environment and all the stressors you have. So each situation is unique. So it is not possible to only have a value. You have to analyze the circumstances. And also you can see as an example, for remediation, that the degradation of a services, of a function, is not related with the number of activity concentration, but mainly for the process itself of the decision-making, the action that you are applying to the nature. So it is important to bear in mind. What you can see in this on the right is, for example, a mapping from the United States for the agriculture government to understand how people relate with natural amenities. And it's taken into account, for example, the weather, if you have lakes, all the characteristics of the environment. And this is very important, and it is, if you see, a value judgment to assign how we can develop social demographic conclusions and how you can use this value for constructing how the environment is related with people. Hope it works. Okay, so this is the second for not, but that in the next slide I will say what are we considering ecosystem services. Also very important, as Andy, he explained about the approach ICRP has very well established for protection of the environment about RAPs and DCRLs. This ecosystem service approach is not the intention to replace this approach that we have for the protection of non-human biota. We are just thinking a complementary tool to make more robust the environmental radiological protection. And maybe we are thinking that will be also very important to use in communication and in decision-making process. Check. And if some of you are aware of ecosystem services, you know there are 3 points that criticize this ecosystem service approach that, of course, we are taking into account in our draft. That it seems, you say, okay, protection of the environment, but it could be seen as very much anthropocentric and not ecocentric. Another issue is, oh, okay, this is very good, but it's very vague definition. So it is possible to implement this approach into practice. And another is the economic valuation. This is one of the biggest criticism because it's assigned a value to nature. Okay, but what is ecosystem services and why ecosystem services? In applying ecosystem services, you know, we are applying natural ecosystem, the many natural ecosystems that we have that provide components of abiotic and abiotic components. And you know, bearing in mind all the services, that you can have many natural contributions regarding development of foundation, the natural resources, the provisional services, the ecological regulations, the cultural inheritance that is involved, and is very much important in human health, the mental, the inspiration, so we can start thinking about the human well-being. You remember the Sustainable Development Goal 3. And not only on 3, so if you see, if we analyze, I don't have time to go in each of it, but you can see they are very much supported, very much related to sustainability, so to Sustainable Development Goals. Okay, why ecosystem services? So we can start thinking this is like a framework of a model. So if we have the possibility to see if we are going to apply some action to the nature regarding radiation protection, we can start thinking of impact 1, or say, okay, this has an impact of some ecosystem service. And then second, this impact could affect human, could affect the well-being, the benefit, thought as a value. And taking this into account, then we can help this in our response. Maybe in applying a policy, making a decision, applying a different technology, and this could act directly to the roots of this situation, of this man-making that can make an impair to the ecosystem. So this is a circle that could be feedback anytime. So bearing this in mind, we start thinking that ecosystem service could be a potential valuable tool. And you say, okay, but how I can implement this? How can I assess this tool? So we can say that we have these 3 assessments. We can say first, the biophysical assessment. So we are going to characterize this ecosystem, the structures, the provisioning, and also other indicators of the ecosystems. Then we have to take into account the social assessment. So which are the stakeholders that are related with this ecosystem, with these components that could be impaired? And finally, you can also do an economic assessment. What happened? What will be the money involved if you lose some of the ecosystem? And this is related with all the services. So trying to think this with the example of the bees. So, okay, as you can see, the bees, as you can know, they're very common and familiar with us. So are linked with various ecosystems, globally distributed. Many in our country also, we use bees as biomonitors, yes, or indicators for migrations, for example, at our atomic centers or nuclear power plants, and also they are used for other contaminants. They are very much used for heavy metals, for example. So they are also, we selected bees because they are very well characterized. They promote biodiversity. As Andy mentioned, it is one of the RAPs that we have in description 108, publication 124. So they can inspire and has an important cultural services also. They are widely applicable, and we are relevant to both approach. And remember, I'm not saying that they will replace the DSRS, they will complement. So they are both from the environmental radiation protection and from the ecosystems approach. We are familiar also. And then, why bees? This slide is to show you in which many services bees are involved. In the quantity and quality of food, in nutrition and medicine, also promote inclusive communities, the biofuels, the forest conservation, healthy and diverse ecosystems. They promote economic opportunities because they are it's important industry by beekeeping, the cultural service, and if we start, you can see one of which is very much related with Sustainable Development Goals. So, taking in mind that this is very much supportive and related to sustainability, we can start thinking of a framework on how to implement this tool. This is just a draft. We are just making This is I can say, the first illustrative or scheme that we are developing. But the idea to you is to show that they're complementary. So we have the environmental common radiological protection and this services approach. So if we begin, for example, from the environmental radiological protection, as you know, and you have the value of the dose rate that you calculate for a specific scenario, then you start to compare with the DSRL that you have, and you can have three possibilities, as you know. You can be above the band, and then you have to take actions to reduce and try to give within the band. Then you can be with the band, and then you can give consideration to apply any action to reduce exposure, and you can be below the band. And this, you can select the most reasonable protective action. So imagine that you select to take an action on the environment. So you say, well, which is, oh my God, okay. So the idea is how this could be, then you start thinking, this affects in some way how humans, we perceive the environment. If it says no, no problem. So you see that the ecosystem services will not be affected. But if it is this, yes, you're trying to identify the ecosystem, trying to identify the services and the benefits. And the idea is that together, you can make an option and decision to the best option based of these two aspects. So this, we are trying to develop also in the draft some case studies. This is a real site, Los Alamos National Laboratory, that can have some contamination in the site and use hives also as biomonitors, okay? So the objective is for them to try to determine the viability of certain radionuclides. The tritium was the only detected. Okay, so imagine that the stakeholders are concerned about this site. First, you analyze the DSRLs and imagine the DSRLs are okay. So from the point of view of publication 124, there's no justification to take actions, but stakeholders are concerned. So the proposal is to have an excavation of the topsoil, but this excavation could impact or could imply the removal of hives, or for example, could affect the bee food. So the idea is how to apply this three type of assessment. So what is the idea to do is, okay, assess, for example, honey production, the usefulness as hives as biomonitors, the pollination and influence, for example, in wildflowers, that I didn't say so much because it's an arid zone, that is an important issue. So try to apply all the metrics of the biophysical assessment. They identify which are the stakeholders that are more affected because of this impair. And then you can also try to make an economic assessment for decision. Okay. So, and this is my final slide. So the idea is to show to you that ecosystem services has a potential contribution and support sustainable development goals. For us, it is not only related with environmental protection, it is we see more as a bridge with human and environment. It's also a complementary tool as the tool that we have today. The idea is to help. It is not an obligation to use. It's just to help in some specific examples, to help in decision-making, in communication, in education. And we are reviewing all these. We are reviewing the existing tools. We are reviewing case studies. We are trying to make more emphasis in how to put into practice this tool. And also, well, we are refining the bees. So thank you very much.
We have time for a question. Yes, in the front.
Thank you very much. Very interesting approach. Indeed, I'm wondering, because as we know, and many, many years ago, I did a study for the European Commission where we looked also on impact of an event on the opinion of the population. And this changes with the scenario. For example, in your approach, do you distinguish between long-term and short-term? Because tourism after an accident is obviously not an issue. But in the long term, it will be. And I think that would be interesting also if you are applying your approach for different scenarios and different timescales. Thank you.
Yes, thank you for the question. Yeah, and of course, that is why each scenario is different, and we need to take into account the impacts that could apply in the short term and also in the long term. And this is much related when I say we have to identify the stakeholders that are much affected for this, that will be different in each case. And also, I know I have just a minute. Regarding the exposure situation, we see this very effective or that contribute in decision making, for example, for existing exposure situations. For example, for the management of legacy sites. It can be applied in other, of course, also in emergency, but this is much the focus. And also we will present some characteristics that could be applying for planned exposure situation, but it is a different type. Thank you.
Any other questions? Yes, in the front. If you raise your hand. Oh, hi, thank you.
Thank you, Analia and Aisha, for your presentations. My question is not exactly related to the last presentation. It is more of a general question. I noticed that for the environment, we are considering all aspects of non-human, but in the Sri Lanka study, I noticed that they mentioned that more depths of cesium-137, the less concentration. So are we considering only like few aspects of the environment in the studies or all of them? And one more supplement question. Are we considering only contamination for the environment or external exposure as well?
Well, we are considering not only, you say contamination, but also from external. Yes, the idea is to consider all the possible scenarios that we have. And I didn't understand so well the first question, sorry.
In Sri Lanka study, they mentioned that the more depth the cesium-137 is, the concentration is less exponentially. So if we are it is less exponentially in the summary. So if we are considering all the environment aspects, I don't fully understand how will this apply over here.
Okay, so you say that you have a level of cesium that is below a certain level. Maybe, Nicole, you want to add? Because I didn't know this study of the Sri Lanka.
It is likely a question related to a poster, so we will invite to discuss it during the coffee break.
Then we can address better in the coffee break. Thank you.
Thank you very much. And we will continue. So thank you again, Analia. And we invite Nicole Martinez, who is a member of the main commission of ICRP and also chair of TG 1-25, you've just heard of. Nicole Martinez is a professor in the Department of Environmental Engineering and Earth Sciences at Clemson Universities in the US, and her current research focuses on dosimetric modeling, behavior, and effects of radiological contaminants in the environment with diverse applications. So the floor is yours.
Great.
Nicole, thank you.
Thank you so much. Now for something a little bit different. It ties into the environment in that the broad environment, as Andy mentioned, and also it ties into interest in effects that ties to the environment. But specifically when we're talking about animals, there are a lot of different contexts where we might think about effects in animals or why we would be interested, and I'm going to give a kind of big overarching view of some of those different contexts. So I'm going to, because we're the system of radiological protection, I'm of course going to contextualize this in the context of radiological protection. Andy and others have pointed out the aim of our system, and also that our system is, the evidence base is science, ethics, and experience, and it has evolved over time with this. And then Andy gave a nice kind of evolution of protection of the environment, or how we consider that. But if you notice the people and the environment, and the first part of our aim there, for people we have a specific aim of protection. So prevent harmful effects that are in principle preventable, and to reduce the risk of cancer and heritable effects to the extent reasonably achievable. Now, people are animals, but you might be saying, well, Nicole, you didn't have a human picture. Why do I mention people here in the context of animals? Why do you think? How do we get to people from animals? Oh, you're here to learn. Excellent. It's research, so animals and research. So this is one reason we care about effects in animals. And so I mentioned kind of different fields. Radiobiology was one of them. So study the effects of ionizing radiation on living organisms, how radiation interacts with cells and tissues, along with the biological consequences. So in this context, we're thinking about underlying mechanisms, and there's this fundamental science behind it, but usually we're interested in scaling the results to people or translating the results to people. So that could be for informing our risk models, that could be more insight into effective radiotherapy. We do sometimes get the misconception that because animals live a shorter amount of time, they don't get radiogenic cancer. Their lifespans are physiologically compressed. So for most mammals, they get cancers around the same point in their life that a human would. There's some exceptions for that, but that's generally the case. Of course, also animal studies give us more information than effects, like for example, biokinetic models use animal data as well, but for this presentation, I'm largely focused on effects. So if we're thinking about this in the context of radiological protection, this is very useful for us, but we're not thinking about radiological protection of the animal specifically, right? Of course, we have animal care ethics, responsible animal care and use, but we don't have the same protection endpoints like we would for the environment, for example, but this is still useful. Historically, there's been ample animal radiation-related research, a variety of endpoints considered. I mentioned cancer, not just cancer, heritable effects, tissue reactions, all of that, and you can see that here. You'll forgive me, these are from the United States because that's the research I'm most familiar with. And I also have mammals here, but of course, there is research beyond mammals as well. So we have the mouse house at Oak Ridge National Lab, lots of research done there on mice. On the bottom left, these cows actually were accidentally contaminated at the Trinity test in 1945. And so they basically shipped these cows off to the University of Tennessee, and that led to a lot of agricultural type research. The middle picture here is on inhalation. You see dogs along the bottom and then guinea pigs in the middle, and you can actually see rabbits along the side because they wanted to prevent contamination of the body because the animals kind of lick each other, and they wanted specifically to see if there was a difference between inhalation and ingestion. And there are lots of beagle studies out there. Gail Wallachek actually giving a lecture in one of the other sessions talked a lot about the benefits that we've gotten or the research from animals like this. And because we've advanced and animal ethics have also advanced, we really need to use and rely on this data because these types of studies are probably not going to be done again. All right, but when we say non-human biota, this is the environment session. we typically think of those reference animals and plants, right? Here are reference animals and plants from publication 148. And indeed, we had people in the environment and that aim. And as Andy said, we want to maintain biological diversity, conservation of species, natural habitats, communities, ecosystems. So this is a different protection endpoint than we have for people. It's still part of the broader system, but we're looking at different endpoints. So, for example, we had radiobiology. This is fundamental understanding of mechanisms. And then we go to radioecology, which is broader than that. We're thinking about the structure and function of ecosystems on the whole. So when we're thinking about protecting the natural environment, we're not concerned so much with one individual animal. We're concerned with how different populations and communities interact and how that affects the environment as a whole. So, in that sense, we're interested in different endpoints. We're interested in mortality, morbidity, reduced reproductive success, things that can affect population numbers, which can go on and potentially affect biodiversity and the overall health of the ecosystem. Research on radioecology can be at the field or lab scale, and actually we really need both. The ecosystems are complex, so research in the lab isn't going to necessarily account for the same complexity that you would have in an ecosystem, but because ecosystems are quite complicated, field research is also going to be difficult to interpret because of all those different complexities. So it's very useful to have both of those pieces of information. Particularly if we are trying to establish benchmarks, we can use both sets of data, one to develop or propose benchmarks, and then if we have other data, particularly field data, we can use that to validate the benchmarks and gain confidence in those benchmarks. There's a nice link, though, between radiobiology and radioecology in adverse outcome pathways. Adverse outcome pathways, and George from NEA is actually talking about adverse outcome pathways in another session, so if you're interested in that, you can speak with him. So they go from basically an initiating or key event on the cellular or molecular level, and then that perhaps can go up and tell you what happens in a tissue, and then the organism, and then we can extend that potentially into populations. So there's a nice, and that's very relevant to radioecology, so there's that nice transition there to something relevant to protection of animals in the environment. But that's awesome, that's great, I love it, but there are circumstances where there are animals in our day-to-day lives beyond this. It could be livelihood, it could be a companion animal, it could provide another kind of service. There's lots of different services animals provide. And so publication 153 starts to kind of get into that. It's talking about veterinary practice and introduces the idea or consideration of animal patients. But publication 146 on emergencies also mentions, livestock and pets also need to be considered in our decision making. So this is a different context where we think about animals and effects in animals. And then I changed my figure on the right here just to emphasize that we're all connected. We're connected to our environment. What we do influences the environment. Our environment influences us. And it's the same interaction with animals. And this can connect to our well-being and sustainable development as well. So let's talk about animals in our day-to-day lives. Here are some examples. A service animal or comfort animal there on the left. In my small town in South Carolina in the United States, there is a local goat farm, and everyone gets very excited about baby goat season because you can go look at the baby goats for free, just run around. And that's a nice community event. We went to the Falcon Hospital here in Abu Dhabi, which was amazing to see those animals. Police dogs, so animals touch our lives every day, right? And we have a responsibility for animals entrusted to our care to take care of them. And companion animals now, and the techniques available, if, say, an animal gets cancer, a mast cell tumor here on the left, we treat it, often very similar to how that's treated with people. And you can see that radiotherapy is effective and the mass resolves here on this pet cat. So all that to say, when this person brings their cat into the vet, they're not concerned about the population of cats, right? They're concerned about their cat. And so we have a different protection endpoint. There's a different context that we're looking at these animals. So in that veterinary context, I have companion animal here, but there are other different animals, of course, that vets will see. And so they're considered from an individual patient perspective. Just like in human radiotherapy, we want to minimize tissue reactions as far as possible to still get that effective treatment. And veterinary people are still the priority because people are involved in those procedures. The staff and such things, but we have a holistic and graded approach, but we also need to consider animal welfare, and this is typically of the individual animal. And that has to do with our values, right? And how that animal connects to us in our day-to-day. Of course, there are connections to radioecology and radiobiology. A lot of that fundamental research on animals, of course, is relevant to veterinary practice. And veterinarians often help in radioecological studies involving animals. So there's those connections as well. What we haven't really thought much about, but I showed a working animal, a police dog. You can imagine if there's an emergency, you have animals helping you. If you want to think about protection, that's kind of an open question. So context is key. That's my bottom line. Radiation effects, we're interested in that for a variety of reasons. It really depends on the context, what that endpoint of protection or what the benefit is going to be. Different motivations for study and understanding, so how we interpret, use, and protect against those effects are going to be different. The last thing I have is that context and shift, and I want to tell you a story about Mabel, the burro, or the donkey. Mabel was found in 1930 in the wild in Colorado in the winter by the United States Army Corps of Engineers. She was a baby. Her mother had died in an avalanche. These soldiers adopted her. She came back with them to the military base, and she underwent soldier training. So she became a part of the U.S. Army. Then, starting around 1945, when we're trying to figure out potential effects of radiological releases, she was shipped down to New Mexico, where she became a research animal, specifically for genetic tests. You know, fast forward a few years after that, her breeding years are over, and they say, well, she doesn't have use anymore, she's going to be destroyed. One of the employees said, well, what if I take her? Sure, no problem. And so this employee took Mabel home. This employee's daughter marries a journalist. This journalist loves this donkey because Mabel the donkey is super good with kids. She rides them around on her back. People are really interested in her story. And turns out she's super old. One of the oldest donkeys. Donkeys are supposed to live to be like 40, 45 years old. Spoiler alert, Mabel lives to be 60. So, not only that, the Guinness Book of World Records comes to the farm. You have one of the oldest living burros, donkeys around. And so she went from a wild animal to a soldier to a research subject to a pet to a local celebrity. And so there are various different things in her lives, and we cared about Mabel for different reasons. And so the context can shift. In this story, in Mabel, when I spoke with Ed Pierce, this is the journalist that reported this story, and people started coming to visit Mabel. He says, this gentle animal should be remembered for her service to humanity and ability to bring smiles to the faces of small children. So this fun story is just to say, yeah, we have this context, but the context is not necessarily static. It can change. And then finally, we do have these differences, but there's a lot of different research going on, and we can benefit. Just because we're in radioecology doesn't mean we can't benefit from radiobiology and vice versa. So we really should learn to sometimes it's hard if I'm talking about an effect and I mean reproductive success and someone else is talking about effect and they're like, oh, I'm just really interested in double strand. Sometimes that can be kind of hard, but if we understand where we're coming from, we can figure out how we can help each other and really make the best use of this data that we have. And I just have 3 examples here of radiation effects databases that I think would benefit from sharing more with each other. And that is it. Thank you.
Thank you, Nicole. And we have time for one question. Here in the middle.
Hello, Nico, and thank you for the wonderful presentation. So I am a radio ecologist and I study the effects of radionuclides if there is any release from the nuclear power plant. So I always wondered, we only take care about humans and environment, and rather than we don't take we don't make a lot of efforts in identifying the radiological effects to the animals, especially wild animals. So this is more of a comment than a question. So what happens is that when you try to evaluate the effects to the animals, it is more easier to do to the environment, because you can keep some detector, you can collect some water, you collect some soil and identify the radionuclide concentration in them. But when it comes to animals, it is more difficult to do that. So I think that is the main issue in understanding the effects to the animals rather than the environment. Yeah.
Yes, I would like to react to that question, or that comment. Thank you for the comment. And actually, the next presentation will be useful for that, I think, as well. But the Frederica database has a lot of information on radiation effects in animals from an environmental perspective. So from this mortality, morbidity, reduced reproductive success. So that's the database that's within the ERICA tool. So the ERICA tool is a tool that's used, I think, largely in Europe, but probably elsewhere as well, that models and gives you an idea of what the dose rates might be, how that might compare to the DCRLs. So there are absolutely tools out there. I would love to see more research, to your point, but there are ways to go about doing those assessments. I think that was the comment, right? Okay, awesome.
Maybe time for another burning question. Oh. Hildegard.
So thank you, Hildegard van den Hoven, Director of the Division of Radiation Transport and Waste Safety of the IAEA. So thank you for your presentation. But I have a question. How would you like to see this also implemented? If we look at, for example, when we were discussing even with our member states, how to include environmental protection globally, and Andy, you gave the definition, which is quite, comprehensive of what we see with environmental protection. And this is suggested that whatever, we have to protect people and the environment, and environment discussed as before, but what we, as presented in the definition, but it was at that time also not acceptable by member states to have a specific protection category for the environment. And you are today also suggesting, if I hear your presentation well, or to have also a specific protection category for veterinary animals. So, but how do you see this implementable at a worldwide scale?
So, great question. There was a reason I didn't put the ICRP background behind my presentation. These are my personal views. And also my presentation is about why we care. It wasn't specifically about what we do about it. So that was just my motivation for why we care about effects in animals. Regardless of how you implement animal patient in the system, people still care about the effects to their animal, right? So that's my argument. In terms of implementation, I'm going to fall back on the classic IAEA approach, which is a graded approach. Like, however this is done, particularly for if we're thinking about animal patients, I consider this to be something that a veterinarian considers, right? So what is a graded approach in protection of the patient? Like as in human, it's the Goldilocks dose you want to meet the clinical objective or I'm not a doctor, I don't know, the diagnosis, and you want the exposure to get you that. Right? You don't necessarily want it higher. You don't want it lower because there's that sweet spot. So it's the same kind of idea in the context of veterinary. So veterinarians are probably largely implementing this in practice, but that's just basically an idea. You should still not think about just getting the prettiest picture in terms of diagnosis. The other question in terms of this broad definition of the environment, I agree with you. I think some of those can't really be assessed, like protecting the carbon cycle. I don't know what that means, right? So I think you ask a very important question, and that's also one of the things we are reflecting on. I'm sorry I don't have a better answer for you right now, but it is an open debate about this potentially a fourth category of exposure for the environment. We can talk more about it later because that's a great discussion to have.
All right, thank you, Nicole. Okay, and so our last speaker for the session is Natalia Simulashkina. Natalia is currently retired and is a consultant in Germany, but she has worked for many years as a scientist at the Institute of Radiation Protection, Department of Radiation Physics at the Helmholtz-Zentrum in Munich, in the Risk Analysis Working Group. She's also participated in and coordinated European projects and IAEA initiatives such as MRAS and Modaria. So Natalia, the floor is yours.
Yeah, thank you. Good morning, everybody. Thank you very much for possibility to present our handbook. And this presentation may be a little outside of the ICRP topics, but I think it's on the right place geographically, because it's, we present you a handbook of radionuclide transfer parameters, soil to plant, for radiological modeling, emergency preparedness in arid environment. You know, this is for each assessment, for each modeling. It could be radiological modeling, or for the emergency preparedness, or the dose assessment. You need solid, good, and reliable parameter. And that was our idea, that ideal these parameters have are derived from direct measurement and in the control experiments on such things. And transfer coefficient from soil to plant has a very important position in each model. So for example, here's compartment model for contamination pathways, but to human health and so on. And this is a really important parameter. You can tell me, in internet, you can find many, many different handbooks, papers, publication about transfer coefficients. Many for IAEA product and as such. But if you look to these publications, you see this is most of this parameter, 99% for the other climate, not for arid climate. And some example in USA, you can find some arid parameters, but not much. It was created a working group in frame of Modaria project from agency, and results of this group, we produced the first, practically first database for this is soil to plant transfer parameters non-temperate environment, one part of the arid environment, and this is TechDoc 1979, and some publications in Journal of Environmental Radioactivity. Now ongoing is a CRP project in IAEA, and also the create a database for the parameters, transfer parameters, but it's only for the natural radionuclides, not for the artificial. The first try to compare die parameters für the temperate climate and for the arid climate show us the big difference, really big difference. First graph is for the cesium-137, and second is for the strontium-90. It's very few publication with artificial radionuclides, but for example, in Syria, very active and can work with artificial radionuclides. Why we do it? Why we make this database? At first, is the development, very active development of nuclear energy in arid countries. You know, here in Abu Dhabi, we have worked already a long time, Baraka nuclear power plant, and it's developed in other countries auch. Very low availability of arid radionuclides parameter, and what is also very important is climate change. You know, in Europe, it will be also drier and drier. And for example, Spain has problems, or Greece, or such these countries. It was also a reason to start and to do it further. That is only a new map of aridity of our Earth. And these arid territories grow with the time, unfortunately. The arid countries in arid environment, there's also very specific contamination pathways. We have, for example, here you have dust storms, was also pathways what you couldn't find in the temperate climate. Very deep groundwater. Also the radiological impact of the oil industry. Also some specific pathways here we can find. How we work? I can tell you this work to search. Sometimes it's really digging. You have to go to the library. You have to look in the internet. Also private communication, as very, very different ways to find some information and some transfer coefficient or concentration ratio for these countries. And sometimes it was really boring work, sometimes it was very exciting. What is the problems to create this database? Most of publications really are work with or dedicated to the natural occurring radionuclide material. Very few work with artificial, with the cesium-137 and strontium-90, and only Kazakhstan is not really arid, but have data about americium and plutonium. Missing also researchers dealing with local plants, for example, palm trees. Now we have a publication from Abu Dhabi, from Khalifa University, 3 publications about transfer to the date palms, palm dates. No information about radionuclide migration in local soils. We have only one work from Kuwait, make some experiments, but no information about the KD values. Few works include soil characteristic and geographical position of sampling sites. Really, we tried to find this name of some village or something else, and it's very difficult to find where is this village. And often the sampling methodology does not correspond to general accepted methods. And they're mostly really only arithmetical mean, and very often without standard deviation. So this is our big problem. What is this? This is database now. We have evaluated more as 800 publications until now. 2,100 entries in the database. Such countries: Syria, Egypt, Israel, Palestine, Libya, Morocco, Iraq, Saudi Arabia, Kazakhstan, Jordan, Iran, Pakistan, Sudan, Algeria, Tunisia, South Africa, USA, and UAE. In the database is 72 edible plants and 21 medical plants. This database can be used everybody, it's clear. It's specific for the environmental scientists, for health physicists, for the dose assessment, for emergency preparedness, or some stakeholders. It's a very, very wide possibility to use this. And handbook is ready already. I can show you. This is a handbook. As a free available, is also free available in the internet. We have here some small flyer with a QR code and address of the internet. Everybody can use it. And I have now some books of this, and if you have interest, you can get it. Okay, thank you. Yeah. What will be good for the future? More control experiments, more experiments in the laboratory. Also more with cesium and strontium. It also could be short-lived cesium and strontium 1885. Experiment on resuspension, foliar contamination. We have only one work as Egypt about the foliar contamination. Migration in soil, very important. Food and fodder transferred to milk and meat of local animals. This exists. One publication in Syria transferred to the camel, on camel milk, and one or two publications of Kazakhstan transferred to the horses, on horses' milk. Harmonization of experimental design. It's very important and present more information about the position or about the samples collection on such things, experimental details. On harmonized reporting and publishing of results. Thank you very much.
We have time for questions.
Thank you for a beautiful presentation. I am working on soil-to-plant transfer factors in the tropical environment, and I know how hard it is to get the. I am working on the soil-to-plant transfer factors in the tropical environment, and I know how hard the data is in arid and tropical environments because we have very less. Now, we are modeling using machine learning and AI tools to have harmonized data without doing without much experiments. Now the problem is each experiment data that is generated in these environments have different parameters. Soil to parent transfer factors depends on lot of soil properties, and not all soil properties are given by each experiment, each lab. Some give pH, some give conductivity, some give ORP, and nobody is focused on exchangeable cations. Now when you put it into the model does not accept because each data point is different. So I want ICRP to urge to have a uniformed reporting structure, like soil properties should be, most of the soil properties should be evaluated during these kind of experiments, and so that we can have a better model.
Yeah, okay, it's not a question, it's a statement,
Yeah.
as I understand.
Any other questions for Natalia? Yes.
Thank you, Natalia. A very insightful presentation. My name is Wang Chenxiang. I'm from the China Institute of Atomic Energy. I learned from your presentation that the most problem of the research on the arid environment is the lack of database. And your main expectations are we need to do more experiments and to get more data. And I have a very naive question here. Is that possible we do the simulate calculation on the arid environment scenario, and based on the theory level, for example, that for the arid environment we have different soil type, and this may be leading to the different soluble rate of different radionuclides, and we may have a different plant type which leading to a different absorbed way. So if that's possible, we do the simulations based on this kind of differences and as part of the database, or because it's a very naive question, or you mean the mainstream way of doing this research is just from experiments? I'm not sure if that's possible to use the simulation calculation.
Here's what we have in the database. Yes, yeah. It's measured data for different local situations, for different local soil. In this database, we didn't do anything with this data. This is pure public how this is public data.
Yeah.
Without average, without nothing. And you can, my colleague can help. You know,
Okay, thank you. Just to answer some of the questions you are raising here. I think it is important to have models. What are models for? They are to predict the transfer for standardized situations. And I think every model cannot replace to do the real measurement. If you have an event and look at the Rhodos system, how does it work? It has also an approach that it combines the models and then adjusts with the measured data. And I think this is the way how you have to treat it. Simulation models are wonderful, and you can play around, you can have wonderful results, which often do not represent the reality. So you cannot avoid to do the real measurement if you have a radiation event, a release event. And I think these are just approaches, and the IAEA is doing a lot in order to cover as many scenarios as possible. But each accident is different. You have different environmental conditions, you have different climate conditions, you have different release scenarios. So in the end, you always have a high uncertainty on any prediction you are doing with a simulation model.
Great. Thank you for those comments. Well, that brings us to the end of our session. Let us again give a round of applause to our excellent speakers. I'm sure if you have any questions, they'll be happy to answer them after the session, so catch them in a coffee break or another time in the symposium. So with that, I would like to end this session and wish you a wonderful coffee break and remaining symposium. Thank you.
Yeah. Okay. Yeah. But I don't have to. Oh, now it's yes.
Well, he will introduce you, so. Thank you again. All right. C'est parti. Good morning, everyone. It's great to see all you here for this session on optimization in imaging radiotherapy, and recurrent imaging. I'm Sébastien Gros, Associate Professor of Radiation Oncology at Loyola University in Chicago. I'm a member of ICRP Task Group 116 on radiological protection aspects of imaging radiotherapy. I'm very happy to be co-chairing this session with Dr. Khalifa Al-Kaabi, radiation oncologist at Taiwan Hospital here in the UAE, and co-founder and general secretary of Emirates Oncology and Radiotherapy Association, who's been a wonderful partner in putting this session together. So over the past couple of decades, we've seen a real shift in radiotherapy from the days where imaging dose was small and mostly ignored, to now, where imaging is central to how we plan and deliver treatments. Modern system gives us diagnostic quality images for sub-millimeter precision, adaptive planning, and even real-time motion tracking. But with that progress comes the question, how do we balance accuracy and image quality with our responsibility to keep patients' doses as low as reasonably achievable? That's exactly what this session is about, understanding those challenges, finding that balance between radiological protection and effective treatment, and discussing how we move forward towards smarter, safer, and more personalized imaging and radiotherapy. So we have an excellent lineup of speakers who will cover this from different angles, clinical, technical, and research, and I'm really looking forward for the discussion that follows.
Thank you, Sebastian, for this introduction. Now moving to the first presentation for the rapporteur summary, presented by Buthaina Al-Amiri. She is an ICRP Task Force 116 mentee and from FANAR UA. The stage is yours.
Thank you, Chairs. Good morning, all. I will go fairly quickly through the presentation of the posters submitted for this session. So we have a total of 14 posters submitted, including one video presentation. The posters were mainly in the area of optimization in imaging in radiotherapy, and recurrent imaging. The flags within the pie chart represent the countries where the posters were submitted from. And obviously, 50% of the posters were submitted from the Gulf region. So in optimization and imaging, the focus was in reducing unnecessary exposure and standardizing protocols in order to improve patient safety. In abstract 289, the abstract focused on myocardial perfusion imaging, where it highlights the importance of using dose modulation tools in order to optimize exposure. Sorry. In abstract 68, the abstract focuses on establishing national diagnostic reference levels in nuclear medicine in Saudi Arabia through collection of data across 22 centers within the country. Abstract 257 provides a video presentation on digital mammography in Sri Lanka and concluded that potential dose reduction can be achieved through evidence-based protocol adjustments. While abstract 120 on Ottawa ankle rules audit focuses on justification rather than optimization, and the study revealed that half of the ankle x-rays were unjustified. Other abstracts focuses on traditional shielding versus modern dose reduction technologies, and remote quality control for mammography imaging can be feasible and affordable for centers, mammography centers. And the radiation, one of the abstract focused on radiation, the effects of the factors affecting radiation exposure during surgery, and suggests modifiable parameters and technological improvements in order to optimize patient safety. Other abstracts focused on the standardization through the use of DRLs in in routine CTs and pediatric CTs. In the area of imaging and radiotherapy, we had one poster in Monte Carlo study where the the study evaluated the use of slapped phantom instead of CTDI phantoms. And the study identified that suitable material for QC is accessible for resource-limited radiotherapy in order to ensure consistent dose monitoring. The other poster was not related to imaging radiotherapy, but rather on the optimal home isolation duration that is required for patients post-iodine therapy treatment. In recurrent imaging, we have one poster which was submitted focusing on the cumulative radiation dose from a repeated imaging session. The study analyzed 600 CTs that were conducted during the COVID-19 pandemic, and it highlights the risk of repeated CTs during the pandemics or disease management. The key messages that were addressed through all papers that optimization in imaging can be achieved through ALARA, DRLs, and protocol standardization, substitution of phantoms in radiotherapy can be achieved in order to enhance patient dose monitoring, and recurrent imaging underlines the importance of monitoring of cumulative dose. Thank you, and you may visit the posters section here at the venue or visit the posters online in order to have more information.
Thank you, Buthaina. Now moving to our second presentation about the role of image quality in optimization for imaging, presented by Mika Kortsiniemi. He's from ICRP Committee 3 and working at Helsinki University Hospital in Finland.
Thank you, Dr. Khalifa, and good morning to everyone. So my talk is about the role of image quality in medical imaging optimization. And to start with, in medical imaging, the adequate image quality can be seen as a fundamental requirement, helping the correct diagnosis. If we miss that, any kind of dose optimization or dose saving is basically worthless. So building from that adequate image quality requirement, we could describe image quality as the main driver of optimization in radiology. Any definition also for image quality should address the clinical purpose. What is the clinical task that we are supposed to perform? Now, if we scan the patient, for example, with CT, there is also a representative abdominal CT image here. We could address the image quality in a traditional way to look for the contrast, noise, which is the graininess in the image, and spatial resolution. So those are the three basics that we qualitatively and quantitatively may determine quite easily, at least from the technical objects. In addition to this, when we have patients who move, there might be metal objects involved. So we also are considering motion and metal artifacts, and also other kinds of artifacts that we might have in the imaging chain. And if we have an elaborate imaging device, we could have more contrast base to cover. We could have, for example, photon counting CT, providing spectral imaging and beyond. But this is more descriptive of a technical or physical image quality. If we think about the factors which affect the clinical image quality, the list is longer. We can surely address these technical image quality factors: contrast, resolution, noise magnitude, and also texture of noise, which has an effect to the diagnostic performance. And these physical factors in turn propagate to more clinically oriented parameters. For lesions, how lesions with different sizes, shapes, and edge contrast profiles will turn out. Now, this is harder to do with the technical fandoms. We need clinical images for this. And then beyond, we have to take into account in image quality concepts, what is the quality factors related to human observer, radiologist who looks at the images. There is concepts coming from viewing distance from the monitor, the medical display or monitor itself, what is the performance of that, and operator noise, basically boiling down to does the radiologist have a good or bad day, or what is the inter-observer variability. If we have an AI tool looking at the images, a diagnostic one, we may skip the free last, but nevertheless, we have many factors, more than just the technical factors. So if we derive a relationship between the technical image quality and how it builds the vertical axis, the diagnostic value of imaging, we can see that with very low levels of technical image quality, there is nothing relevant to see. And then again, if we push that too much, then we already see everything that there is to see. We don't gain any other value in y-axis. But this is not all. Actually, the worst limitation in technical image quality is that it's not very representative for the diagnostic value that we have. There is uncertainty. We cannot describe all the characteristics of pathologies, how they represent in diagnostic images with mere technical factors. So what we need to do is to build bridge from technical to more clinically relevant descriptors of image quality. How we do that with this brief presentation, I just mentioned the essential ones. So we have already a long time ago established mathematical model observers to really describe how we can describe a certain diagnostic tasks. For example, lung nodule with a certain diameter, with a certain contrast towards the background, how it can be seen with a certain model observer types. Recently, we have begun to use more comprehensive artificial intelligence tools to measure clinical image quality in a more relevant way. So if we replace the x-axis, technical image quality, with more clinically relevant metrics of image quality, we might have more relevant relationship between these two axes. We have the clinical context here. And also the role of image quality measured and built in a more clinical level will give more role for optimization. So we have a leverage. I mentioned that we have been developing also AI-based tools for image quality measurements. And I showed just a couple of examples. There are many. Actually, we can use the AI tools very flexibly in different kind of algorithms. So in the left here, there is an example of good image quality criteria evaluation in projection radiography, plain chest X-ray images. So the deep learning algorithm can evaluate the collimation edges of the pictures, how the geometry is represented, and also the inspiration level within these images. We do in our organization roughly almost 1 million projection radiography exams per year. So with these kind of tools, we might have a comprehensive evaluation of the whole production volume of diagnostic images of patients. The other example is the noise measurement directly from CT images in this case from the lung region. So we have quite a good coherence between the ground truth and the deep learning-based estimate of image quality. Why I also show this is that we actually target the clinical image noise measurement to the lung segments. So we seek to provide these image quality metrics for relevant tissue structures so that it can also drive optimization in a more meaningful way. If we look optimization process and actually the whole imaging process as a whole, we can see how image quality has a role in different steps in this process. And also actually these stair steps show also the use of artificial intelligence in this context. So we don't actually begin from optimization. The first step is referrals and justification. With the advanced clinical decision support systems, we can utilize better the large-scale hospital and radiological data that we have for the patients, and therefore direct the patients more accurately and at the right time to the right modality to be scanned. But the role of image quality here is more to define the what question or answer to the what question. What kind of images we seek to have, and what is the gross image quality level we want to have. Then, after successful referral practice, we can connect that to protocols that we use in imaging modalities. And in those protocols, we should use optimized imaging parameters. And with these parameters actually answer to the question how the image quality we seek is actually achieved.
2 minutes.
Yes. Going further, we can, for example, in CT use 3D cameras for patient positioning. Also that has a connection to how we can actually improve image quality. In this case, for computed tomography, AI-based methods for projection radiography exist for the same target to improve also image quality, but also radiation dose. Image reconstructions and enhancements can reduce noise, improve motion compensation, and many other factors for image quality. And that's also how we can then utilize it for optimization. In parallel with the image enhancements and all the preceding steps, we should also be able to measure image quality and connect this image quality evaluation, like noise maps here, to the dose aspects, so the radiation exposure of the patient, to be meaningful for the whole optimization process. Image analysis is then the real review part of the radiological exam. That's the diagnostic task of the radiologist. But there we have also many tasks that can be leveraged through artificial intelligence. So that answers the question why we need to have a certain level of image quality. And also, with the AI tools like segmentation in this image analysis step, we can feed the image quality measurements more meaningfully to the right target organs. Then finally, clinical predictions and care decision support can also include further diagnostic procedure recommendations. Also there we have connection and role from image quality to drive these recommendations in a meaningful way and to feed back into all parts of optimization. So we can conclude that imaging is increasingly guiding healthcare. Further, image quality is guiding imaging techniques, and this is the core of the optimization process. But if we want to have this optimization working, we must be able to measure clinical image quality objectively, quantitatively, and automatically. This basically needs algorithmic tools for large-scale, consistent, and comprehensive optimization. So this is the direction I see we should go. With this, I thank you for your attention.
Thank you, Mika. We'll be moving to the next session for the sake of time. For the second presentation will be about radiation oncologist perspective on challenges with imaging dose optimization and radiotherapy, presented by Dr. Nadim Pervez. He's a consultant radiation oncologist at the Gulf International Cancer Center here in UAE.
Thank you, Dr. Khalifa, for introduction. Since I'm introduced already and time is short, and thanks to Dr. Mika, who actually solved some of my portion of presentation, so I can fill it faster. Just to move. Yeah, here. Okay, so here today I will talk a little bit about introduction, then key challenges from radiation oncology perspective. We'll give you just a couple of examples of clinical context, and then future direction, and with the conclusion. So radiotherapy cannot be, the modern radiotherapy cannot be without imaging. Imaging is the integral part of radiation oncology treatment today. Many times I say to my radiation oncologist colleague, a lot of improvement in our field is from the medical physicist, like some present in the room, and also some radiologists, and actually that make the revolution in our field. So we work together as a team, of course, but there is a bigger role of the medical physicist. So I must acknowledge our medical oncologist colleagues in here. So there are, foundation of modern radiation oncology, as I mentioned, is based on the imaging. So it actually, we have a lot of different changes than when I was a resident. It was very different era. Sometime I was doing hand marking for radiation treatment. Then maybe X-rays come, fluoroscopy came, and it changed now completely. And if I would not be keeping up with the pace, I would be an obsolete radiation oncologist. So you can see that how imaging play a role. CT played a big role where now we can plan and deliver treatment based on 3D CRT, IMRT, SPRT, you can name it, all those new technologies. With this, if you look into, I just give you one quick short example. When we treat the head and neck patient, head and neck cancer patient, their glands, salivary glands come into radiation field, and when they survive, if they survive from cancer, they suffer all their life with dry mouth, and it's really challenging, very difficult. But we're dealing with different other, the different method to challenge that as well. But actually, by using imaging, by using new technology like IMRT or SPRT, we are reducing those xerostomia or dryness of mouth and make their quality of life better. So if they survive from cancer, not to suffer from the side effects. So there is the fundamental challenge is the balance. Where would we balance? If you ask me as a radiation oncologist, sorry to say, I should not say, but sorry to say, I don't care about the imaging dose, sorry. And when I see my colleagues who are in radiology and how strict they are, then I see, I think about cancer only and my radiation dose is very high, but I'm not fully correct. I'm not fully correct because, okay, I understand. Cancer to escalate the dose and as much as we can. At the same time, can we not apply the principles of ALARA in other part of the body? Like, imaging is not only tumor area, it can be bigger than that. So there have to be a balance. I'm thinking to move myself towards that balance. At the moment, I'm not. And what are our challenges as radiation oncologist dilemma when we come to imaging? So if you look into that ALARA principle, of course, that we should adopt that in the imaging, then we should actually targeting, we should have there are differences now in the low dose and high dose type of treatment, multi-dimension changes we have. We have changes from low to high dose, we have change from the volume, we have change of the volume and change of the technique of the treatment, and they all are different. So we are like almost a bit lost
where to apply which principle, and it's not going to be easy when we start cleaning up all that. What our challenge is, we go day by day for the treatment. And day by day is okay for that day. For that day, whatever radiation dose I'm giving because of imaging, I don't mind because I have to deliver that radiation. But the cumulative dose is another challenge. If we treat patient with 25 sessions of radiation, you can imagine 25 sessions means it may be even more than once per time, and that per session, and that may reach up to 50, average is 45 to 50 images per patient. So that's the cumulative dose which we need to focus how we can change and reduce. And actually we're doing that because when we're fractionating shorter fractions, then we are moving that direction. So it's very complex, that what we do is very complex. Our work is complex. Sometimes we do KV images, sometimes we do CBCT images, sometimes we do, for same session, multiple CBCT images, other time only one image. Some people do one image every time, and some other people do one image once a week. So it's a complex field. So somewhere we have to start, take it from one end, and start working on it to how to improve that. So we should not be. There are times I felt that when we think about ALARA principle and radiation exposure, and not thinking about the cancer, which can actually, if not controlled, kill patient, So sometimes I have to be very tough on my radiographer, saying that can you please ignore this ALARA principle here and just move forward for the patient. So the team dynamics is very, very important here because we're working like a team, and like anybody else, team is very important. So for the team, we are radiation oncologists, not focusing much on ALARA principles. Then radiographers, they do, medical physicists, they do. And they're a radiological protection team or people, but the collaboration between them or coordination or communication between them is not the best today, at this time point. So to improve that. Then we have many centers. I've worked many centers. I'm traveling around for the radiation oncology. My experience, I'm learning from it, but I saw many centers without any proper protocol. So wherever I go, I check, is there a protocol or not? And then we start working on the protocol. That's the bare minimum, that must be there. What about training requirement? Things are changing. Are we training our staff? I don't see that many often. Sorry, I'm complaining more than being positive, so being honest. So then there are biological uncertainties. There are, as I mentioned, low dose rate, high dose rate, variable radiosensitivity among the patient. There are genetic components, there are genotype, phenotype, and they're all different. It's difficult to predict that, but we should have some models. And as Mika mentioned about the AI, we can use that to predict things for us. And then we don't have some long-term studies. There are a few imaging studies which actually establish surveillance role in the radiation, but not all. We have lots of research options. I will, for the time's sake, I'll go for that. The most sensitive topic for me is the pediatric radiation oncology, radiotherapy treatment. They are the most vulnerable. I can read that out to you, but no need to save the time. They have longer life to live. They're more sensitive, and they have more potential for long-term complication. So they are the one which show you the result. There are some palliative patients, we treat them, they don't survive long enough to give us the complications of radiation. But the pediatric patient, they do. They will show you why we should look into the ALARA principles for them. And then, so cumulative work. So the another example, and there's one more example, and that's it. I'm not going to go there. Are many examples can be. So radiation is another challenge. The people who deal with radiation in any form by technologists or physicists or radiation oncologists, they know that when we're going to retreat the patient, they are very different scenario now. Because of previous radiation, we have less chance to give more radiation, anatomical changes, tissue tolerance around the tumor change as well. So there are lots of challenges there. And then for the new baby in the home is actually newer technologies like PSMA PET scan we do regular. I do regular for prostate cases now. Before was not. Adaptive radiotherapy we're doing a lot, and that may involve the repeat imaging. Then the proton and heavy ions are coming into play, and do we know about that, how to handle those challenges? We don't. MR, but there are solutions for it. When we're going to shorter fractionation treatment, we do less imaging. So we do have some advantages. MR, LINAC come into the field, radiation exposure go down. So there are pluses and minuses, so there are things which are moving in a good direction, others are more challenges for us. So for the future, Mika mentioned about the AI, we should use AI, help us, what is the optimal imaging, when to stop, how much to do, and we can do it by automated quality assurance, like right while we are treating the patient. So there are tools should be developed which actually help us. At the moment, we don't have those, but we are going that direction. With this, I will come to my conclusion. I'm trying to keep the time, and sorry for shortening and going fast. That imaging is, there's nothing new, which I said before. Imaging is essential for modern radiotherapy treatment, but cumulative dose of radiation, which by the exposure of imaging, we should keep an eye on it. And effective optimization requires professional collaboration between all the MDT people, what we call it. We cannot work alone. We have to have radiation oncologists, medical physicists, radiation technologists, radiation protection people to work together as a multidisciplinary team. LRA principle must be accepted, adapted as much as possible, because there are times which we need to overrule. That we need to think about a patient cancer cure more than anything else. And there are emerging technology like AI should be utilized that I have no doubt that can reduce the exposure of the patient. This will be the best thing for us. These were my references, and with that, I'll say thank you, and I finish a few seconds before. Thank you.
Thank you, Nadeem. I know some might have a few questions, but we'll leave that at the end of the session. So moving on to the next presentation with recurrent imaging and adaptive radiation therapy, ART, presented by Evan Williams. He's from ICRP Committee 3 and Arpansa, Australia.
Good morning, everyone. And I'd just like to respectfully acknowledge the traditional owners and custodians of the country throughout Australia and their continuing connection to land, waters and community. And I'd like to pay respect to their cultures and elders past and present. In a similar fashion, I'd like to thank UAE and FANA for inviting me to this presentation. And let's go. So today, I'm going to give you a bit of chat about adaptive radiotherapy, why, where it comes from, but also how to audit it. How do you know it's doing what you think it's doing? We're going to get into MRI LINACs with that, and then a potential future. So recent background. Conventional radiotherapy at LINAC from about 1960s, utilising more or less 2 gray per fraction standard conventional therapy. About. Right. And the LINAC beams are shaped with a collimator or blocks. It's static, there's no movement. Computer planning is pretty simple. It's limited by the CPU. A single Monte Carlo calculation back on an old 486 might take a few weeks. Dose accuracy is limited. Your grid's about 5 millimeters, which gives you a resolution of something more than that. And portal films are being taken. And that's pretty much as close as you get to understanding with any degree of accuracy what is happening to the patient at time of treatment. And then things changed. Because LINAC technology improved. And one way of looking at this is a degrees of freedom argument. Essentially, every single component of the LINAC changed. Collimators became multi-leaf collimators, and they were dynamic. Onboard imaging appeared with KV using planar, but also KVC cone beam CT. And then we have an idea of a definition of adaptive radiotherapy is defined as changing the radiotherapy plan delivered to a patient during a course of radiotherapy to account for temporal changes in anatomy or changes in tumour biology or function. And I think that stood the test of time quite well. And if you just want to get a brief idea of the difference between a KV image and an MV image, that's actually a more modern MV unit. This is about a 2010 image, and so it's considerably better than images taken in the 2000s. So, sorry. So adaptive radiotherapy can be applied more or less at 3 time scales. Between separate fractions, and that usually happens with a new planning CT, time and effort intensive. Immediately before a fraction, this is known as online because it's being performed while the patient is on the bed and on the basis of the image of the patient on the day. But then we also have an intra-fraction capability now, which might be real-time tumour tracking. And why do you need to do this? Well, let's say you are using a hypofractionation approach where you are delivering, say, 26 Gray over 2 fractions, 13 in each. You're using an IMRT approach with, say, 5 gantry angles. You really need to know where the tumour is for each of those gantry angles, because with a 2 millimetre or sub 2 millimetre risk space and 13 Gray fraction, you've got no room to get it wrong. There's no central limit theorem with 30 fractions where you can correct. You have to be right. So, imaging within a given fraction. And the other thing, of course, we have to talk about is MRI-Linacs, where you have soft tissue information. So with the CT Linac, there's roughly 2 vendors, same as MRI-Linac. It's pretty much standard equipment on a modern Linac these days. An MRI-Linac is specialised equipment with very high adoption costs, very high resource operating costs, but it gives you wonderful soft tissue contrast. It gives you dynamic and functional imaging. If you're trying to do analysis or understand how well these things work or doing research to get a large enough data set, an MRI-Linac is actually quite difficult. And also, of course, there is the ionising dose component of the CT on the Linac, which is not on the MRI-Linac. So how do you actually do it? And how do you know whether you've done it right? So I'm going to break this down into 2 basic... Oh, sorry, my slide set is a little bit different. The other thing you've got to be aware of on the MRI-Linac is there is a very strong magnetic field, which means nothing metallic can be in the room. You also have modifications on the dose because of the magnetic field, which also means you have modifications on the measurement of dose within an MRI field. And also the helium levels, which is something we learnt, can actually impact how the field is behaving. So is your art working? Well, let's have a look at different ways. There's 2 general ways of understanding what's going with a patient on the bed if they aren't set up correctly. One is that the actual tissue, and particularly the tumour, has modified in shape, and that we call an adapt to shape problem. Or the geometry of the patient is the same as the planning CT, but they are not in the same place relative to isocenter, i.e. relative to the planning system of how they were originally set up. So more or less, if you're on board imaging, you are trying to merge or equate that image set to the original planning CT one way or another. And here we have an example of a CT image of the phantom used by the Australian Clinical Dosimetry Service to verify anatomy, positioning, location. Now in the central circle, there is the capability to put film. So you can take a real-time dose measurement of the film during irradiation. Now if we just go, can I go back a slide? Yes. So how the audit works is that you send the facility to be audited, the phantom, but you also send them some contours to place on the phantom. And the one you send is this. Here we go. Well, it's the pink ellipse. They are sent the data associated with that contour automatically, and they fix it to the data set, which they obtain under their planning CT, which you can see here. And then we have a MRI acceptable phantom, which of course is made of plastics, so you can't see the plastics, but there are water-filled components within it. And they're also water-filled straws, as you can see down in the vertebral body, which allows you to align and set up your phantom appropriately upon image matching. You then can see the correct and unadjusted, red circle, which is in the middle of the phantom and which is a perfect match, or should be perfect match, to the setup of the planning CT. Upon imaging, they find out that the ellipse is not actually the same as the phantom in front of them. And so they have to do a real-time adapt to position, recalculation on the bed, however their process is, and then treat according to that. And then the other setup is that the phantom is deliberately offset by the auditing team which gives a set of parameters for to adjust the position on the bed to actually correct the position of the phantom so it matches the CT data set. And this is what comes out. So up the top, we have the films. In the middle, we have a difference map. And down the bottom, we have a formal analysis where you can identify the shift and a gamma analysis and the distance to agreement between the film as imaged on the unit and the planning system prediction. So what has actually come out? This is a real example, real audit example that was performed earlier this year. This has been presented and reviewed at the Global Harmonisation Group for Imaging and Auditing in Radiotherapy. And here you can see the difference map, the prediction of the actual individual traces through the cardinal axes and the trace on the left. The gamma criteria on this one was 5% 2 millimeters. We can put whatever we want into that. We have the control of the spreadsheet and the analysis. And then on the right, you get the transformation matrix, which is produced by the system on the basis of a difference agreement between the imaging on the day and the planning system. Oops. Right, so what's happening in the future? I'm going to talk a bit about dose here. A cone beam CT on a LINAC delivers something in the order of 2.5 millisievert, plus or minus about 1, depending on the geometry, the anatomy, the detector resolution, etc. The method of reconstruction of the image for the day can be done in multiple different ways.
1 minute.
And the future of reducing that dose but still aligning or demonstrating appropriate alignment of the patient on the day with initial planning CT is inevitably linked with a lot of different IA tools, because you use a sub-data set of imaging but still has enough quality, enough information to allow a high precision match with the planning CT. So we also need to recognise that in a lot of this trying to demonstrate the system works, the accuracy of the tools being used is often limited by a lack of information, statistical reconstruction problems, and to really prove that these systems work in improving patient outcome, gathering enough information from a large enough patient body is also a challenge. And so just for a few references, if you're interested in reading more on this and to chase it up, I'd look at these. Thank you.
Thank you, Evan, for this talk. Now moving on to our next presentation about DRLs for CBCT optimization, presented by Barham Alai. He's a director of medical physics at Radiation Oncology Department at University of Minnesota, USA.
Good morning. Thank you, Dr. Arkabi, for the introduction and for the organizers for the invitation. So I'm switching focus a bit here this morning and talk about the COMIM-CT optimization and the need for the dose reference levels with that respect. So for those of you in the audience who are not familiar with the COMIM-CT, that's basically the most widely used imaging modality that we employ in radiation oncology these days. Pretty much all the radiation delivery systems have a COMIM-CT on them. Most of them these days are kilovoltage COMIM-CT. So they are often being used, as Dr. Parvez mentioned, without regard to additional absorbed dose, because we want to treat the patient correctly. We want to give the correct dose to the tumor. We want to spare the organs at risk. And we want to use them for margin reduction and dose escalation. So essentially, our number one goal is to treat the patient correctly. The imaging dose oftentimes takes a secondary nature to that. With that said, we cannot ignore the imaging dose magnitude. So this is a chart of the different imaging modalities we've been using since the onset of radiation oncology with the megavoltage films and all that going down the list to the COMIM-CT. And there's a wide range of absorbed dose to patients from these imaging modalities. Of course, these are per fraction. The one that is a focus right now is the kilovoltage COMIM-CT, which is the one that we employ the most, as I mentioned before. These are all estimates of a dose, depends on the patient size, depends on the technique used and all that. So these are not LINAC outputs or imager outputs. As you can see, the kilovoltage COMBIM, there's a range I have here, 0.1 to 4 centigrade per scan. The reason for that, besides the fact that the patients are different, is the imaging protocols used are different. So this is a sample of the imaging protocols, the default ones, used on a variant TrueBeam. And there's a similar chart for the Elekta system out there. And as you can see, going from a low dose to high dose imaging protocol, there's a 67-fold increase in imaging dose. So again, oftentimes, again, as I mentioned before, these protocols are used without regard to the patient dose. And oftentimes, we can change the protocol if needed. We can actually use a lower dose protocols and get the same outcome as we can get with the high dose protocols. So, and that's what we're trying to establish here, that we need to optimize the imaging dose. Our colleagues in imaging have been doing that for many long time. There are many protocols, many initiatives out there, like Image Gently, Image Wisely, and all that, that actually advise diagnostic imaging to optimize the imaging dose, use lower dose protocols, and adjust them per patient, essentially. In therapy, we don't do that. In therapy, is one protocol for all, pretty much, depending on the site. So again, the imaging dose optimization, which is often reduction, is warranted, of course, for reducing dose to patient, to reduce the chance of secondary cancer, for example. And it's a lot more important for pediatric and young adult patients, as was mentioned previously. And hence, we need to optimize, customize the imaging protocol according to patient size, whether it be a BMI, body mass index, or patient separation, or some other metric. It can be done, and we should be moving toward that goal. And there is, on that respect, there is some work done. This is from the report of the astrophysics work group on the ICRP that was published in 2025, recently actually. And they do mention imaging optimization is critical, particularly for pediatric patients who are more radiosensitive and typically survive longer than adults. But they mention that optimization is not just reducing the imaging dose. We need to pay attention to image quality. And that was previous speakers talking about the image quality. That image quality, if image quality is too bad or too low, lowering the radiation dose defeats the purpose. We end up imaging the patient twice, for example. So we have to be very, very careful with the image quality and balance it with the imaging dose. And that brings us to the need for dose reference levels for Chromium CT, which we do not have at the moment. These is the same acronym as the diagnostic reference levels for diagnostic imaging, but we use dose reference levels, and I think ICRP 116 actually talks about that. But going back to 2018, AAPM Task Group 180, which I was a part of, we actually, in the title of that, we talk about dose reduction. So we were thinking about this back then. We weren't using optimization per se, but we did mention that we need to create local imaging protocols with image modality, technique, and frequency that suits the patient, the treatment. And again, develop pediatric-specific protocols and follow the ALARA principles as much as we can, basically. So imaging dose reduction, it can be done. There are many examples of that out there. I have a few here. As an example of that, this is actually for a 4-year-old patient that was treated with 11 fractions. Had we used the adult imaging protocol, which is on the left, that one on the left is the adult imaging protocol. You can see the dose volume histograms of the patient. This is hard to see, but anyway, dose volume histograms at the lower left. And the patient would have received the different organs between 30 and 35 centigrade. Now, in this case, we don't use that for pediatrics, of course. We use a HEAD protocol, and that cuts down the dose by a factor of 20 over 20, just by doing that. And the image quality is fine, because the patient is smaller, of course, is a child. The same thing is I borrowed it from a colleague in UK. Actual patient, 4-month-old being treated, they actually reduced the imaging dose by 95% over several successions after reducing the imaging dose by reducing the current time product and the extent of the field and all that. But the question is, if you do that, would you get the same outcome or not? So this is a study that we did. It's a phantom study, obviously. What we did, we actually reduced the imaging dose by, in this case, cut the number of frames by 2. And we looked at the image matching algorithm. And the variant TrueBeam systems, they have this algorithm that actually matches or registers the images, the daily images to the planning CT images. And we wanted to see if actually reducing the dose, does it affect that? And it doesn't in this case. These are, of course, based on bony anatomy matching. These are not soft tissue. And as you can see at the bottom, the dose reduction was about more than half, but the image image registration was the same. So nothing was affected adversely. The same thing for the thorax phantom, again, the phantom, and that, again, the same thing. More than half of image reduction dose, but again, the shifts were the same. So it didn't affect the integrity of the image registration by the system. I have an actual patient image here. This is the left arm. And again, the protocol, the standard protocol in our clinic is a spotlight for this. So we've been reducing that by changing again, MAS on this. The middle image is about 50% dose reduction, and the one on the right is about 3/4 reduction. And all of these, again, the goal here is to see the bony anatomy and the outline of the patient. We don't, because while we're treating the bone, we don't care really about the soft tissue, because you can see a streaks on the image, right? The images are not as good, but it serves a purpose, and all of these images were approved by radiation oncologists. So you can actually very easily can be reduced by simply reducing the MAS or number of frames in some instances with the same outcome. Now moving on to the dose reference levels, which was a topic of this. There is a first-of-its-kind study done by IPEM in UK that was published last year. And actually, that's what they did. They did a study in order to produce DRLs for Chromium CT. What they did, they actually had a survey for UK institutions performing Chromium CT. They actually asked them to measure the dose CBDI, which I get to in the next slide, and they're providing information for 7 treatment sites. And they use the data to establish national DRLs. So what they did, I mentioned the CBDI, for those of you who are not familiar with that, essentially is an adaptation of CTDI, which has been used for CT scanners since the 80s. It's not the same because, again, we don't have a helical movement. It's different modality of imaging. But again, use the same phantom, head and body phantoms. Again, measure the dose with a 10 cm ion chamber at the center and periphery, and come up with this metric of the output of the unit. Again, and they did weighted CBDI, 1/3 of the center of 2/3 of the periphery, similar to the CTDI. And this particular UK study, they requested the institutions to measure that using this metric and report it again in the total exposure in total dose normalized to the milliamp second. So whatever they got, milligray divided by 100 MAS. So that's the data they collected from the institutions. And then there's some more data. They actually asked for the normal KBP, MAS, and all that. Whether it's a bow tie filter was used or half a bow tie for the variant units, F1 or F0 filter for the Electra units, the extent of the field, the different cassette plates being used, the craniocaudally defines the image volume. These are M2, M10, and M20. And again, with trajectory, whether it's a full scan or half a scan. So they collected all this data from different institutions, collated that, and they came up with these tables.
1 minute.
And that's a table, measure CBDI values. Again, there's a value, there's an interquartile range to indicate that. And then they have for 7 clinical indications. So these are all the data they collected, and they said they can be used for setting national DRLs. So additional observations about the same study, again, spread of measurements was very tight because the systems are very similar to each other. There's a narrow range, and there is a significant variation in optimization strategies. Some places do that, most places don't do that. So that's what we're trying to bring across here. And then for the recommendation, they call about optimization for the clinical task, optimize the field length, field of view, and so on, protocol for patient size, and develop patient-specific protocol, and use of the published DRLs, which will help in the optimization process, can benchmark them, we can set the standards and all that. So in conclusion, establishing DRLs is a necessary step to promote standardization and optimization in combined CT protocols. This can be started at national level, like a UK study did. The methods and tools require attention. They use a CBDI, it doesn't have to be that, it could be something else, frankly. And the size-specific imaging protocols need attention, especially for pediatric cases. And thank you for your attention.
Thank you, Baram. Now moving to our second presentation about smarter scans, safer patients, AI-driven imaging dose optimization, presented by John Damilakis. He's from ICRP Committee 3 and from University of Crete, Greece.
Thank you very much for the introduction. Hello, everyone. Okay, so AI is becoming a key tool in patient dose management, patient dose optimization, so it can support the justification process, predict doses, improve image quality, segment organs, and also can support reporting. This paper was published in European Radiology recently. Authors provide insights from a 7-country audit, and this graph shows percentage of fully appropriate, partially appropriate, and inappropriate exams. 15 to 40% of exams, total exams in those countries, are either partially appropriate or inappropriate. So the question is, can AI reduce non-indicating radiation exposure? The European Society of Radiology, the Royal College of Radiologists, the American College of Radiologists, they have published referral criteria, they have developed tools, clinical decision support systems. The ESR has already incorporated AI algorithms So this is a nice approach to reduce inappropriate referrals. Computed tomography reconstruction. In the early 70s, the CT reconstruction was filtered back projection, very reliable, fast, but to produce low noise images, you need high doses. That's why in 2009, iterative reconstruction algorithms were developed. The only problem, texture, the plastic appearance of the images. So that's why machine learning-based algorithms were developed in about 2000, 2001. This slide shows this plastic appearance. The noise level diminishes, but with a major change in noise texture. So deep learning CT reconstruction is a supervised technique process. The input image is generated by a low quality, noisy sinogram. The output image is compared to ground truth, and the neural network learns by adjusting various parameters via back projection, image noise, image texture, resolution, and so on and so forth. And the ultimate goal is to get to produce images as good as the ground truth. Can deep learning-based CT reconstruction reduce patient dose? It is still early, but findings show that the answer is yes. So this is an example, CTPA, pulmonary angiography, performed on a pregnant patient. And as you can see, the effective dose is very low. The DLP only 14 units. So this is really a good indication that doses are low using deep learning reconstruction. This is a very recent paper published in Radiology, use of AI in cardiac CT and MRI, and the authors, they consider all aspects, patient selection, workflow optimization, image acquisition and reconstruction, image analysis, denoising, detection of incidental findings. This is interesting, an interesting area. A risk stratification imaging report. So, and of course, dosimetry. Dosimetry is one of the pillars of AI, sorry, the pillars of medical radiation protection and radiation protection in general. We have taken several approaches. In the interest of time, I will avoid providing details, just few words. So we use personalized dosimetry for organ dose estimation as a ground truth. And we follow, of course, the workflow, the machine learning workflow, data acquisition, pre-processing, feature engineering, model selection, training, testing, evaluation, validation, deployment. It is a long process. Collecting data from PACS and then anonymized data. In my department, we have developed a PACS dedicated to AI to collect data in an organized way. This is very important for artificial intelligence. And then, of course, we label data. And this is the most important, probably the most important step, pre-processing. So to clean the data, otherwise garbage in, garbage out, transform, ending up into values ranging from 0 to 1 for comparison, and dimensionality reduction, which is a process of transforming high-level data space into low-dimensional data space, latent space to avoid redundancy. Okay, I'll give you an example. This is, well, this is one of the first papers we published, a methodology to train and deploy a machine learning model for head CT. Just to give you an example of the basic principle. So the main point here is to develop the feature matrix with independent variables, and the dependent variable statistics is the basis of machine learning, of course. So in this case, most of the The independent variables are data coming from DICOM metadata. Hounsfield units is not a part of my DICOM metadata, so we had to apply a mask binarized image to exclude non-patient voxels. And then those images, the dose values, the dependent variable is coming from the masked dose map. If you are interested in this topic and AI in general, tomorrow we'll give Mika and I will give 2 talks on AI in medical radiation protection, on image quality and dosimetry. DRLs is a useful tool for dose optimization. Many countries have established DRLs, but they also need to update the DRLs at regular intervals, at least according to the European guidelines. We need to update at a minimum frequency of 5 years. Is it easy? The answer is no. And AI can be used to establish and update DRLs. This is an example we used in the vascular aneurysm repair as an example, and the method is based on those reports with the noise, resize, and then we use AI-powered OCR methods, optical character recognition, in order to retrieve info useful for DRLs. Rhythm is a new project, started 8 days ago, October 1st. It's the new kit. Of course, Rhythm is an acronym. The full title is Radiation Health Safety and Quality for Youth, a comprehensive approach to justification, optimization, and education. One of the main work packages. It will keep me busy. It is a European dose and image repository using AI methodologies. So that's what we are planning to do, to develop a repository based on AI methodologies. And of course, there are challenges. There are opportunities, there are methods, nice methods and techniques, but there are also challenges related to explainability, ethical and legal challenges, regulatory challenges, financial, technical, education and training. What does this photo show? A woman, blonde woman, with black framed glasses, and just above them, another, that's the same image, the same woman smiling with blue glasses, right? Do you all agree? We are all wrong. Illusion. Illusion. So this is the Thatcher effect. So according to Wikipedia, is a phenomenon in which changes to facial features are difficult to detect when a face is upside down, even though the same changes are obvious in an upright face. And I uploaded this image to see if LLMs can recognize the distorted green. What do you think? Have LLMs recognized the distorted green by raising your hand? How many of you think that LLMs recognized? Okay. The majority is right. So Gemini, this is, the answer is the reason I failed to recognize the green is due to a phenomenon called the Thatcher effect. So LLMs are like us. We train LLMs. I'm showing this. This is related to biases, right? We are biased. We train LLMs. So no surprise. They can also they are biased. So LLMs, the architecture is quite complex. They see and interpret images using the CNN, convolutional neural networks architecture, and fully connected neural networks. The fully connected neural networks are responsible. They get the features detected by CNNs, and then they process, and they are responsible for the special arrangement of features. And they failed. So large language models training data, like human experience, is heavily biased towards right-side-up faces, There are issues with image quality, there are issues with biases, and other challenges. Thank you.
Thank you, John. Now moving to our last presentation of this session about balancing accuracy and exposure toward optimized use of daily KV CBCT in IGRT, presented by Zakia Rabi. She is ICRP Task Group 116 mentee and from the Royal Hospital in Muscat, Oman.
Good morning. It is my pleasure to stand in front of you today and be a part of this amazing event. My talk is about optimizing CBCT. Actually, I'm going to share with you our experience toward optimizing CBCT. Before I go to the core of this presentation, I would like to give a quick introduction. IGRT, especially CBCT, is one of the crucial tools that is used in radiotherapy to ensure the geometric accuracy of treatment delivery. On the other hand, CBCT modalities are associated with radiation doses, which means that extra doses to the normal tissue. So there is a strong need to balance between the advantage or benefit and risk of using of a CBCT, which is actually a challenging task for many reasons. When we started to work to optimize the CBCT, we faced many challenges, and one of the major challenges is the absence of comprehensive guidance for independent optimization. So at that stage, we don't know what should we do and from where we have to start. So we started from the conclusion of this study, which is say that cumulative imaging doses are affected by 3 key factors: imaging modalities, imaging protocols and techniques, and imaging frequency. Imaging frequency, which is meant to reduce the number of the CBCT for the patient taken during his treatment course. There are some centers who is performing verification imaging for the first 3 to 5 fractions, and then weekly or even less frequency for advanced technique. It is a straightforward and easy strategy, but especially in the busy centers with a limited expertise. However, such a clinical decision should not be based on operational concerns. It should be driven by a combination of clinical, dosimetric, and practical concentration. So I found this paper, that a clinical decision to reduce the CBCT frequency without compromising treatment accuracy is based on the assumption that systematic errors are identified and corrected in the first few fractions, and BTV margins covered random errors. So when we decided to investigate the feasibility of reducing the frequency of the CBCT imaging, we think the first step is to evaluate our current situation. So we started from assessment to assess our treatment accuracy. How we did that? By evaluating the six-dimension registration or matching between CBCT and planning CT. Online, which means that this evaluation done before treating the patient, and offline, which is done after treating the patient. In this retrospective analysis, above 3,600 CBCT scans were reviewed. Systematic and random errors are calculated. After that, we calculated the CTV to BTV margin. And these are our results. There is no significant difference were observed between online and offline registration. We found that systematic errors and random errors for for all sites, treatment sites, in XY direction, it is less than 0.2 millimeter. And for rotational direction, the uncertainties in all sites were less than 0.5 degree. Then we applied these systematic and random errors and calculated the BTV margins. And we observed that BTV margins for all sites is less than 0.2 millimeter. What we are doing in our center, that BTV margin is ranged from 3 to 5 millimeters, and that depends on which site. But these results give me that I can reduce my margin even less than 1 millimeter. This means that I'm going to spare my normal tissue. These results just provide me a general indication of a treatment accuracy in our department. Treatment accuracy in our department is very high, but this does not mean that, or this does not give me the clinical decision to reduce the number of CBCT. Still, I have to evaluate our online registration, which is evaluate the setup errors. And these are our results. As you can see, the systematic errors and random errors for most of the sites are more than the tolerance. It is more than 1 to 2 millimeters. If I apply these systematic and random errors for the BTV margin, I will find that most of the sites, I need to increase the margin for the most of the sites, BTVs, to more than 1 centimeter in all directions. So we decided to just focus on the sites where systematic errors and random errors are within the tolerance, which is brain, head, and neck cases. But we observe something, that even with these, or even that patient setup errors are within the tolerance, I need to increase the margin for the BTV in head and neck cases for more than 6 millimeter. At that time, I was thinking if there is any published papers or any work have been done to get something like figure of merit, which is quantitative value that is balance or correlate between image quality, image dose, BTV margins, systematic errors, but I couldn't find anything. It was just brainstorming. So we focused on the brain. But what will be the alternative methods? KV? Okay. KV, it has a positive or advantage. At the same time, there are some limitation for doing KV portal, which is you cannot do a rotation correction automatically. You have to do it manually. So to compensate this issue, we take 2 oblique KV image. Then we decided that to reduce a number of the CBCT to the first 5 fraction, and then twice per week complemented daily KV portal imaging. These are our results. When we compare online setup errors based on CBCT matching with the planning CT versus KV portal imaging matching with the planning CT, we will find that they are in good agreement. There is no big difference. There is a slight difference with the rotation. And this is the treatment accuracy. It's very high treatment accuracy. Then I read this paper, and it is very interesting when they mentioned that small positioning errors can change the overall dose distribution. So we decided a little bit to expand our work and study the impact of, or dosimetric impact of setup uncertainties on target volume as well as on the organ at risk. These are our results. When we compare, when we compare dose distribution with the setup errors taken from the CBCT and setup errors taken from the KV portal and superimpose it with the original plan, which is a plan approved by the ROs for treatment, we couldn't find any difference. And this is the DVH. We selected some organ at risk, and then we see that a curve superimposed with the original plan. So these results provide us confidence to adopt reduced CBCT frequency as a strategy and using KV portal as an alternative registration method to minimize imaging dose for brain site. Actually, we did imaging dose quantification as a part of TG116 in a phantom, and then I quantify the dose for the real patients by taking the advantage of the radiation dose structured report, which is a new feature in Varian, and with the help of third-party software, which is MicroDICOM. And these are our results. There is a significant reduction in the dose from the imaging if we compare it between KV and CBCT. Actually, this is not the end of our story. This is the beginning. In the future, we are going to optimize or take advantage of these recent publications to optimize the KV, to optimize our CBCT protocols and techniques. At the end of this presentation, I would like to thank my team, and then I would like to thank you for your good attention.
Thank you, Zakia. I would also like to thank our esteemed speaker for sharing their expertise and immense knowledge with us today, as well as Sebastian for co-chairing this session as well. We have few minutes for a couple of burning questions. The speaker can come to the stage in here. Anyone has any question in here?
All right. I have a first question, actually. So Nadim and Param were talking about optimization for complex cases. And Param, when you mentioned in terms of optimization, you want to reduce the dose, but there are also cases where we have to increase the doses, especially for those complex. So can you elaborate in some of those complex cases where you have to increase the dose but try to keep it LRR, especially when you start to have to deal with hypofractionated schedules?
I believe I heard your question correctly. You were asking about the instances when we have to increase the dose. There have been instances that the image quality with the standard protocols were not adequate for the purpose at hand, and again, for larger patients, for example. In those cases, we actually had to use a higher dose protocol. It does happen, but it's not often that happens.
Thank you. Anyone in the audience has any questions? Otherwise, I have a nice list of questions for you guys. So, I have a question for Mika. Mika, you mentioned the use of model observers for diagnostic radiologists. So in radiotherapy, we have radiation therapy technologists. Their task is to align patients based on those images. So how would you, so my questions for you is what about building some of those model observers for radiation therapy technologists' task, and how would it be different than building it for radiologists, for example?
As a first thought, I would actually not consider model observers to replace technologists in radiotherapy workflow. The primary use of model observers is really to gain clinically relevant description for image quality measurement so that we can, for example, model how the lung nodule could be detected in certain image quality level. So it's more radiology related issue and not a workflow in radiotherapy.
So let me add, so my question was more related to optimization. Let's say, Param was talking about, let's say, reducing dose. And, in radiotherapy, we cannot use the patient as test subject. So I guess my idea was like, can we use a model observer to try to, simulate radiation therapy technologists who would evaluate image quality and decide what would be an appropriate image quality for, let's say, aligning a patient for lung treatment versus aligning a patient for, prostate treatment, and try to define what would be the most optimum image quality for that patient alignment task.
Sure, in that sense, the analogy is there, obviously.
Thank you. Anyone has a question in the audience? Please raise your hand. Oh, microphone is coming for you. Thank you.
Thank you for the interesting, insightful lectures. So it could be a comment/question for Professor Demalik regarding the use of ML in dose reduction, CT reconstruction algorithms. I think we need to verify that because vendor often, that's the selling point. They sell us that it offers a dose reduction. So I think we all need to verify the fact and better understand the setup of the protocols actually on the machines. So that's a point. My other point to Dr. Zakia, so all the measurements and study was to check patient alignment versus the CT simulator that was done initially to do the treatment planning, right? And you chose to focus on brain, which is good. I mean, less motion, all that. But what about shrinkage in the tumor itself? So these measurements will not address that part. So these are the 2 points that I just wanted your input on. Thank you.
Well, time is up, so I will be very brief. Yeah, I fully agree with you. We have some preliminary data in our hands, but it is still early. Nothing is perfect in this life. So everybody was very enthusiastic about the iterative reconstruction. I remember in 2010, and then some limitations started to appear, and there were some concerns. So we need to wait and get more info before implementing this new technology.
And I'm glad to show an example tomorrow about the shortcomings of even a commercial, quite reliable deep learning-based reconstruction. Thanks.
So, regarding to your question for the brain, you mean that, okay, what we did is online evaluation, and then immediately we have to do offline evaluation. If there is any shrink, immediately RTTs inform ROs.
So when you refer to shrink, you're referring the PTV shrink?
Exactly, PTV
Okay.
shrink.
Okay. Okay. Thank you.
I guess by that we conclude our session for today. Thank you, our speaker, for sharing your knowledge with us today. And thank you for your attendance. Please give them like a round of applause. And you can enjoy your lunch today. Thank you for your attendance.
Good afternoon. We shall start. I'm going to be introducing myself. My name is Mohammed Tahlak. I'm medical physicist at Cleveland Clinic Abu Dhabi and the president of Emirates Medical Physics Society. And my co-chair colleague here, David, he's the chair of Committee 3, ICRP, and he's from University of Dundee. So we're going to be starting today the Medical 2 session with Zakiya Al-Arabi. She's a senior specialist medical physicist with the National Oncology Center at Royal Hospital in Muscat. Thank you.
Thank you, and welcome to the session 12, which is about proton therapy, proton and heavy ion therapy, emerging therapies, second primary cancer. In this session, there is about 5 posters and 1 pre-recorded videos, and participate countries from Saudi Arabia, Spain, USA, UAE, and Germany. The first poster, and these are the key words in this session. The first poster is about poster number 169, which is boron-induced dose enhancement in proton therapy and Monte Carlo studies. The aim of this poster was to investigate using boron-10 as radiosensitizers in the target volume to improve dose distribution during proton therapy. The next poster is video poster 284, application of ICRP pregnant female mesh phantom for fetal dose assessment in radiotherapy with a proton and photons. The aim of this poster is to compare a fetal radiation dose exposure from photon and proton therapy using Monte Carlo simulation based on ICRP pregnant female phantoms. The third one is poster 48, authorizing first proton therapy center in Saudi Arabia. In this poster provides valuable insights and lessons learned on managing complex facilities, emphasizing risk assessment, stakeholders coordination, shielding evaluation, and radiation protection for workers, patients, and public. Poster number 292, advancing ion beam therapy in the UAE, a comprehensive regulatory and strategic roadmap. This is presented by Fanner. This poster shows the development of a regulatory rule book and strategic roadmap. Poster number 293, optimization of radiation therapy dose to well-defined target volume. Fanner stated that advanced imaging and confirmed radiotherapy techniques are crucial for accurate volume delineation, optimal dose delivery, and improvement therapeutic ratio by sparing normal tissue. The last poster is poster number 83, epigenetic regulatory mechanism in the context of radiogenic nephropathy. In this poster, which is from Germany, radiation therapy to the kidney can trigger chronic inflammation and fibrosis, regulated in part by epigenetic mechanism. One key process involved the radiation-induced replacement of histone H2A with the H2AJ. Thank you.
Thank you, Zakiya. It now gives me great pleasure to introduce to you Professor Wesley Balch from the University of Florida, who's well known to many of you and has been a mentor of many of you. Wes was a member of C2, continues his work in computational methods, but is here today to tell us about second primary cancers following radiotherapy, the comprehensive evaluation by UNSCA, of which he was the lead technical writer. Wes, over to you.
Thank you. I appreciate the invitation to speak at this presentation. So this is the members of our expert group. This is the most recent UNSCA report. So a little bit of history. So the topic of second primary cancers after radiotherapy was brought forward by the French delegation prior to, in around 2017, 2018. The expert group was put together. The committee endorsed the plan in 2019. In 2020 and 2021 annual meetings, we reported on our literature review. In 2022 to 23, we reported on draft components. We were given 1-year extension to finish. We revised radiobiology and dosimetry chapters in 2023, and then the 2024 meeting, the report was finally accepted. So let's go through a couple of the chapters highlights. I don't have time to go through the whole report, but one of the chapters is on oncology, and one of the interesting things was the presentation of case studies. And so we started with a simple case study, and then we went to more complicated case studies with the focus on, well, did radiotherapy cause the second primary cancer? So this first case was second primary cancer angiosarcoma occurring in a radiated area for a previous treatment of a breast adenocarcinoma 10 years earlier. And this was considered to be unambiguous, in that it appeared in a high radiation field. The person didn't have any known genetic predisposition to this cancer, and there was no chemotherapy. So it was a pretty clear-cut case that radiotherapy was the cause of this second primary cancer. We then go into more complicated ones, and so here's an example of a second primary lung cancer developed at the site of radiotherapy received 13 years earlier for the first primary cancer was breast cancer. In this case, there were 3 possibilities. Radiotherapy could have caused the second primary lung cancer, could have been the chemotherapy. This patient underwent combination chemotherapy and radiotherapy, or it is possibly plausible that it was a de novo. The lung cancer just happened. And wasn't tied to the previous chemotherapy or radiotherapy. And then the last most complicated case was case number 3. And so this was a patient that had been treated with both chemotherapy and radiotherapy for 3 other primary cancers. At this point, she presented with therapy-related myelodysplastic syndrome, and there was genetic analysis was pretty clear that in this case, which would have been the 4th cancer, was radiotherapy induced. So what are the takeaway messages from these case studies? Well, case study 1 is the prior radiotherapy used in the treatment of the first primary cancer clearly was the indication of the second primary cancer. But radiotherapy was only one of several possible causes of second primary cancers in the other 2 case studies. So it is a complicated matter. Moving on to radiobiology, the key aspect that I want to highlight here is what is the role of chemotherapy, right? So chemotherapy may promote the development of second primary cancers by inducing mutations that lead to cell transformations or by inhibiting the immune system, thereby weakening the ability of cancer surveillance of the body. Conversely, chemotherapy could reduce the risk of second primary cancer by eliminating radiation-damaged cells, or in some cases, such as breast cancer, altering the hormonal status of the survivors through ovarian ablation as an example. So here there's evidence in both directions. Chemotherapy can either increase or decrease the risk of radiotherapy-induced second primary cancer, so the interaction of chemotherapy and radiation. Our 4th chapter was on dosimetry. So as you know, treatment planning software, TPS, is used in the course of radiotherapy to compute the distribution of doses delivered by the radiating device in the planning treatment volume, but also the surrounding tissues and those delineated at organs at risk. This calculation is performed using the CT image of the patient, which in most cases is partial body in extent and only includes the PTV and nearby organs at risk. Limitations of the TPS and the lack of a whole body image, CT image of the patient, hinder the possibility of computing a body-wide distribution of doses, including distances, tissues that receive radiation scatter radiation far from the treatment field. Recent studies have indicated the distribution of out-of-field doses produced by imaging procedures, and there was a lot of talk at the previous Medical One session on imaging dose, undertaken for diagnostic planning and patient positioning purposes can be comparable to the distribution of out-of-field doses, especially for protons and heavy ions. It is therefore necessary to consider the distribution of whole-body doses from medical imaging systems when we do a whole accounting of second primary cancer risks. Efforts needed to develop treatment planning systems capable of delivering computing doses to the whole body. Additional treatment planning should seek to optimize risk by incorporating the probability of second primary cancer occurrence in the process. Right now, we only do a single optimization, balancing organ at risk dose to below thresholds for deterministic effects in maximizing tumor dose. You can envision a time in the future where there's a second level of optimization to lower the risk, the stochastic risk of second primary cancers, and that would be particularly important for young adults and certainly children. So just a quick little side note, how can we do this? Well, here's one workflow that is being developed in our laboratory. You could have the patient planning CT or potentially MR images. There's AI auto segmentation software, so you can completely create a voxelized or even a mesh version of the portion of the patient anatomy from the treatment planning CT or MR. At the same time, you can go to a phantom library and pick a height, sex, height, and weight matched whole body mesh phantom to match to the patient. And then as showed in the center, you can essentially replace part of the whole body phantom anatomy with the patient-specific anatomy, and then you have extensions from the whole body height and weight match phantom. So in the end, you have a whole body phantom. You then do a Monte Carlo reconstruction of that radiotherapy, and you can then log organ doses in all regions of the body. So this infers that the anatomy in the abdominal region is coming directly from the CT. We're also working on a pipeline, AI-based pipeline we're calling Tetramorph. In this case, a patient-specific voxel phantom does not permit preservation of enhanced anatomical features that would be in the whole body mesh phantom. So for example, what if you had intra-organ blood vessels and maybe very small tissue layers? You would never see that in the patient-specific CT voxel phantom. They're already present in the height and weight match phantom, but the organs are not in the proper location or size and location. So in Tetramorph, we use the patient's CT image not as the final anatomical model, but as a three-dimensional deformation guide applied to the patient-dependent or height-weight matched mesh phantom, allowing these features like intra-organ blood vessels and small tissue regions to be brought forward. And we have an example here of morphing the ICRP reference mesh phantom into a patient-specific mesh phantom. So the CT image is not used as the anatomy, it's used as a deformation guide. Okay, so final epidemiology. So we identified 995 non-duplicative articles up through September 2020 with no early cutoff in our literature review. These were through initial screening of abstracts. We got that down to 335 articles. And then we looked at those to see, okay, well, which have sufficient data, including dose at the site of the second primary cancer, that we could do a meta-analysis of risk. And we end up looking at 7 locations. So we had hemopoietic and lymphoid tissues considered together. We looked at, and these are all the second primary cancers: sarcoma, breast, lung, gastrointestinal organs, thyroid, and brain. So the general methodology of the meta-analysis, we applied this through several subgroups. So we looked at all studies together, even those that have potentially overlapping data, meaning they're sharing cohort members. We looked at only studies reporting a linear ERR per unit dose. We also looked at studies exclusively in childhood, exclusively in adulthood, patients without chemotherapy, radiation only, with chemotherapy but adjusted for chemotherapy, and then exclusively external exposure. So, for example, no brachytherapy. So let's look at one example. We have the 7 different examples, but let me show you just a little bit of the example of breast cancer. So this is breast cancer as a second primary cancer. So we have some studies that had estimates of dose, but not individual reconstructed dose. 2 of the studies actually had individualized dose estimates for their radiotherapy dose reconstructions. So in these data, we had more than 20 second primary breast cancers that showed for a latent period of about 30 years, the cumulative incidence was about 20%. This is a table from the report, and I've shown your attention to the last 2 columns, cumulative incidence, and then the time frame in years, essentially the latent period. So studies reporting latent periods between the radiation treatment of the first primary cancer and the second primary cancer are shown in this table. The shortest was 5 years, but the longest latent period was 37 years after the treatment of the first primary cancer. Here we look at studies identified in the literature that report risks of second primary cancer with respect to relevant breast doses are given here. Some studies were found to have overlapping data since they analyzed data from the same cohorts. To prevent biased meta-estimators of the combined risks, references to overlapping data were identified. This is a graphical table looking at the risks of second primary cancer per unit dose to breast estimated in the primary analysis. And if you look at the final, the random effects model, we have a ERR per gray of 0.12, confidence interval of 0.04 to 0.21. Here we're looking at the analysis. So at the very top, we have the pooled data, primary analysis. Then we have 2 sensitivity studies, and then we have the different subgroups, childhood only, adulthood only, no chemo. So what are the findings for the breast cancer? 16 studies identified in the literature provided information on second primary breast cancer to the breast after radiation from the first primary cancer. Studies described had either a cohort or nested cohort design and were conducted in countries in North America and Europe. Cumulative incidence rates after radiotherapy, usually reported in the literature at 25 to 30 years, was generally seen to vary widely, as low as 3% to as high as 26%, depending on the first primary cancer. So this breast is the second primary cancer. The first primary cancer could have been multiple different sites, right? In particular, the highest cumulative incidence were reported for Hodgkin lymphoma, which was up to 26%, and the lowest was childhood cancer survivors, generally under 3%. The latent period from the treatment of the first primary cancer was from 8 to 36 years. Most studies reporting latent period around 20 years. Although information about the shape of the dose-response relationship for second primary cancers is limited, available data in the studies indicate in this evaluation suggests the relationship does appear to be linear and increases with dose. And this is consistent with what was reported from Unscare in 2000 and 2006 reports. We also have estimates of what we call the sign share of the risks, or probability of causation. Sign share usually represents the probability that an observed cancer was caused by the preceding radiation exposure and can be calculated from the excess relative risk. And here we show examples where at the site of the second primary cancer, what would be the sign shared risk at 100 milligray, 1 gray, 5 gray, up to 10 gray, obviously getting closer to the primary tumor target. estimates of ERR per unit dose from radiotherapy tended to be significantly lower than those from other types of epidemiology studies for the outcome first or second primary cancers of hemopoietic and lymphoid, and the whole range of doses from 0 to 10 grays. Such a discrepancy could be indicative of a nonlinear dose-response relationship. So let me finish with overall conclusions from the report. So we did a literature review. We found sufficient information was found in the open literature for looking at the 7 primary sites for second primary cancers. The meta-analysis reported risk for all solid cancers combined was not considered, but we did do an analysis where we combined at least the 7 that we did have individual risk estimates for. Overall excess risk per unit dose for all second primary cancers was estimated to be 0.08 per gray. This level of risk suggests that while patients who have undergone radiotherapy have a slightly increased risk of developing a second primary cancer, the overall magnitude of the risk remains small. This implies that radiotherapy contributes only a minor fraction of the total second primary risk in these patients. Various limitations, insufficient data available in the literature for some of the sites, so we were limited to the 7. The exception of a few studies, the risk associated with radiotherapy reported in the literature were calculated on the assumption of a linear dose-response relationship. The expert group is continuing to look at possibly doing nonlinear dose-response modeling by meta-analysis, and that's a new technique that is being developed. It is not considered currently feasible to draw firm conclusions on things like the effect of age at first radiation treatment, age at risk, smoking status, sex, and other treatment-related factors. We just didn't have sufficient data in the literature to do that analysis. Except for GI cancers, the risk contributing to this primary meta-analysis were in general either adjusted for co-treatment of chemotherapy or were done, occasionally we'll have studies where there was no chemotherapy. The ERR per unit dose calculated in the meta-analysis were compared to risk from other studies, like the atomic bomb survivors. The ERR per unit dose estimates by the meta-analysis for the 7 are generally lower than risks reported from other types of epidemiology studies. For sarcoma, they were about statistically comparable. For thyroid, the statistical compatibility depends on the choice of the comparative risks. But hemopoietic, lymphoid, lung, GI, brain, breast cancers indicated for the patients treated with radiotherapy, those risks were generally statistically and significantly smaller than reported in other radiation epidemiology studies. So this was surprising and actually good news. Our final statement to the General Assembly was the following. On the basis of relevant review, the committee is aware that between 5 and 15% of cancer survivors may develop second primary cancer. The committee considered only a small portion of the total second primary cancers were likely to be attributed to radiotherapy. The annex on second primary cancers after radiotherapy has refined the committee's general understanding of how many of these second primary cancers can be attributed to radiotherapy. In view of the significant benefit of radiotherapy, the cancer survivors, in our opinion, should not be dissuaded from undergoing radiotherapy solely on basis of concerns of developing a second primary cancer. Nevertheless, future design and development of radiotherapy should involve dedicated efforts to reduce that second primary cancer risk. So, and this is members of our expert group, and I thank you for your attention.
Thank you, Dr. Bolch. We will take the questions at the end of the sessions. So we're going to welcome Dr. Ivan Williams. He's the Chief Medical Radiation Scientist and Medical Radiation Branch Head within the Australian Radiation Protection and Nuclear Safety Agency.
Thank you. So today, I'm talking to you about emerging risks, emerging trends in radiotherapy. And first off, I'd like to just respectfully acknowledge the traditional owners and custodians of country throughout Australia and their continuing connections to land, waters, and community, and I'd like to pay our respects to them and their cultures, elders past, present and emerging. And thank the UAE and FANA for arranging this workshop, this conference, and inviting me to present. So, this is what we're going to talk about, what just happened. Then we're going to talk about small fields, and then really small fields, and then fast delivery, and then really fast delivery, and just the concept of the rate of change of clinical practice over time is a whole lot faster than the rate of change of patient outcomes over time. Now, this isn't new, but it's just worth considering, and then look at a potential future. Okay, so that wasn't meant to happen. Let's see. No, okay, so what just happened? We've had a colossal increase in CPU, GPU, i.e. calculating capability over the last 10 years. 20 years, we're talking at massive increases in speed of data. So you can calculate things, Monte Carlo calculation of radiation dose. We've had the massive increase in the ability to hold data. So what it means is we have the computational capability to exploit technical advances on a LINAC, for example. Now, what I mean by that is your modern LINAC now has dynamic capability in its collimator, in its gantry arc, in its pulse rate, or in its energy beam output rate. We can do modelling of tumour prediction. We can model normal tissue effects. We can look at tracking motion, uncertainty parameters, and the QA pretty much of every single item of equipment you've got, and as well as putting together really enormous research databases which can then be analysed using, again, fairly intensive computational techniques. We can do contouring atlases, but all of this, it needs ethics and oversight to demonstrate that the product of these tools, which are often black box, are accurate, but also that we have patient consent to perform what we want to perform with that data. Because the commercialization capabilities of some of these are vast, and so I think there's an inherent requirement from an ethical perspective to understand what we're doing, how we're doing it, and the consequences of what we're doing, not just in the clinical sense, but in the wider social, environmental, and social license sense. So I just mentioned what happened in the technology space. We can now, in real time, using inverse planning systems, but due to the machine and motor control capability, we can change the rate of angle of the gantry rotation space. It can be stopped, halted, moved, column rotation, likewise. Multi-leaf collimators are now dynamic, current beam current dynamic control, all the onboard imaging capabilities. We can also do a real-time calculation of the day from data, from anatomical information which was taken while the patient is on the bed. This is really only possible because of advances not only in CPU, GPU, the ability to perform calculations, but also the way in which the calculations now performed are basically better than they have been previously. There are statistical reduction approaches and many others, all of which have enabled us to simply do more and better things. And it's also had an increase in the different modalities of treatment, again linked to technology, IT capabilities, and also mating or joining together imaging and therapy units such as the MRI LINAC and the PET LINAC. So these are now all in play right now. From a clinical radiobiology perspective, because the quality of data collection has improved, if we think about Amami's publication in 1991, it's the really first rather large delivery and discussion of wide population-based consequences of treatment, but also how to optimize fractionation. Then we have Quantec, more in the volumetric data, conventionally fractionated data, and NTCP modeling. It's free to download. It's a great guidance tool. In 2010, when it came out, it was the subject of conversation for many years. Most recently, we have high-tech, which is the next edition of this development, which is tissue and tumour impacts for hypofractionated radiation, but it also has standards of reporting. And this is also becoming more and more important, because if we don't know what just happened to the patient, we can't understand why what happened to the patient, collate it, report it, and put it together, and then learn from it. And then we have Pentech, which is the most recent, which is sort of high-tech equivalent, but in the pediatric space. And again, free to access, all online, all just a really amazing data set. And just to unpack some of what you get in the high-tech space, we have the pooled international data here, 26 normal tissues. So if we go from left to right, we go through EMAMI, Quantec, and high-tech. We can see we've got the NTCP in high-tech, all online, all useful, all good for clinical guidance. So if you're thinking about introducing a more modern equipment with more modern approaches in therapy, this is a great place to start to give you guidance and understanding of what is good as possible, really, large-scale pooled international data. We also have therapy integrated with immune and systemic therapies, so this is an ongoing thing as well. Makoto will be talking about radioimmunotherapy, so I'll just leave that there, but just understanding that radiation therapy is being developed and techniques to actually work with and enhanced by the human immune system. We have all the onboard imaging. We have MRI-guided radiotherapy, 4D, functional imaging, dose painting based on the functional imaging, radiogenomics, so we have biomarkers leading to optimized dose and personalized fractionation, there's potential as well as predictive biomarkers. This is not what hasn't happened. This has happened. This is in play right now. So I'm going to do a deep dive into one technology, and that's flash. So we talked earlier about super high dose races, super high dose rates, and very small beams. This point is where we're just talking about really high dose rates. So let's have a look at flash. Nominally, flash is at 40 gray per second or higher is a definition. But if you unpack what the beam structure or the pulse structure of a flash beam looks like, the instantaneous dose rate is far higher than 40 gray per second. So we have different approaches of flash, which we'll come to, which actually have different pulse structures, depending on the instrumentation, the machinery, the equipment which is used to deliver it. Now, all these approaches are termed flash. So how do we measure the dose rate? Calorimeters and ionizing chambers are usually what people would use in this space. Calorimeters are very precise, very accurate, very good. Because they work on change in heat, being a calorimeter, they're actually very good for high dose rate approaches. They're quite sensitive to that. They're actually very difficult to control. I look after one of them in a primary standards laboratory. The analysis of measurement is real. It takes a while. They're expensive and they're resource intensive. And it can often take about 2 to 3 days to get what you'd call a measurement using a calorimeter. Ionization chambers, we're used to them. Ease of use, familiarity. They've got good international protocols. But they've got protocols at a standard LINAC dose rate pulse structure. They require calibration. How do you calibrate an ionization chamber that's designed for 200 monounits per minute for 4,000 or 40,000 equivalent per minute? Specialized designs have been brought out, with some of them with quite high voltages or high potential differences across a narrow gap with specialized designs. And the other thing, what we don't know about flash is how it actually works. I think I'm happy to put that out there. Why does it work? Is it the same for everyone? If a flash beam stops in mid-treatment, what do you do? How does flash add up multiple treatments? Can you fractionate flash? Can we measure accurately the dose and the dose rate? And what is accurate enough to really predict and understand patient outcomes? And we're not necessarily talking about a week or a month. We've just been hearing about second primary cancers decades after the event, if delivery is interrupted. cannot recommends. So this is the perspective of Paige Taylor. Now she works with IROC, Imaging Radiation Oncology Core in Houston, and this is an example of the sort of work and understanding that we should have for really any new technology, but specific into the flash space of the sort of things we need to have an understanding of to understand flash. So, have technical advances improved patients' outcome? Indisputably, yes. There is no doubt that complications from radiotherapy and advanced doses and all the rest of it have improved. Here's some examples, and I think we really need to recognise that as a take-home method. Not only does radiotherapy work, it is getting better with the application of technology into the space. Over the last few decades, we've seen enormous increases in technology which have been applied into every aspect of treatment and all the contributing pathways that result in the treatment of a patient in radiotherapy, which have improved outcomes. And we also need to understand that our full understanding of the consequences and how all these processes work is probably beyond our understanding at the point of introduction of the technology. But for us as users and also thinking about patient safety, it's incumbent on us to develop as greater understanding as fast as possible so we can really understand what is happening and that a given treatment path is justified. And it's also worth noting that given the data structures that we can now work with, there are opportunities to hold, save, record data, contribute to pooled international data sets, which will give a greater understanding of how these new technologies work faster than ever before. Thank you.
Thank you very much, Ivan. Again, we'll take questions later, so thanks for your presentation. If we have time for questions. It now gives me great pleasure to introduce Makoto Hosono from Kindai University in Osaka, Japan. Makoto is a nuclear medicine physician and is a previous member of ICRP Committee 3, where he contributed a significant amount of his expertise, and he's now a member of the main commission of ICRP.
Thank you, David, Mohammed, for your very kind introduction. Today I'm going to talk about emerging trends in internal radionuclide therapies. And my talk are three major topics: the new therapeutic radiopharmaceuticals and production of radionuclide, and also clinical application, the radiological protection. And ICRP has already delivered a report dedicated to radiopharmaceutical therapies, and our ICRP publication 140. The title is Radiological Protection for Radiopharmaceutical Therapy, and in this report we are highlighted safe and effective radiopharmaceutical therapy, and also the importance of dosimetry-guided personalized therapy. And the authors, the chairs are Yoshihari Yonekura and Soren Matson, and Wes Bolchi was one of the very active member of this task group 101, and I really appreciate the effort of Bolch. And well, when we look at the history of theranostics, the radiopharmaceutical therapy started in around the 1940s, and Dr. Saul Heltz is one of the founder of this method of radiopharmaceutical therapy. When he started radioiodine therapy, there was already a cyclotron which was functioning in MIT, and Dr. Saul Heltz pushed the people in the cyclotron to produce radioiodine for the therapy of our patients, especially for hyperthyroid patients, and the trial of radioiodine application was quite successful. And also for therapy of thyroid cancer, Dr. Sedley and his colleagues worked on injection of radioiodine to thyroid cancer patients, and it was also effective. So I would say these trials in 1940s are the very beginning of theranostics approach for us. And after the foundation of theranostics concept, this field has been making progresses, and especially for these 2 decades, there was an evolution of this technique approaches of theranostics. We would say theranostics is a combination of words, therapeutics, and diagnostics, but it actually is not only the combination of words, but also it's really an ideal combination of compound against the tumor, and also our radionuclide, which is suitable for cancer treatment, and also we need some good chelating agent between compound and the radionuclide. And as Ivan already mentioned, this is the good drug delivery system to cancer cells. One of the very good example of theranostics perspective is the method for our neuroendocrine tumors, and we use somatostatin analogs conjugated with daughter chelate and the radionuclides such as lutetium-177, which is very effective for cancer treatment. And this compound binds to our somatostatin receptor on the neuroendocrine cancer cells. And this is the example of reports which mention the effective application of radiopharmaceutical therapy radio-labeled somatostatin analogs. And they need a very well-designed clinical trial to get approval of this approach. And the name of the very famous clinical trial is NETA-1 trial, which involved the patients of neuroendocrine tumors of mid-gut net. And this clinical trial has a design or comparison of lutetium dotatate and the standard care, that means non-radioactive somatostatin analogs. And the result was remarkable. They demonstrated the reduction of risk of disease progress by 80%. This result was amazing because usually using non-radioactive anti-cancer drugs, such remarkable reduction of risk can't be observed. And the iodine-131 and lutetium-177 are beta emitters, and we are now focusing on alpha emitters, for example, actinium-225 or statin-211. And I also mentioned that the radium-223 is already approved for prostate cancer with bone metastasis. And the alpha emitters are an advantage of high LET, and which is very high effect, biological effect for cancer killing. And this is the, one of the results of actinium labeled daughter date, which is alpha emitter, and they reported the good results of treatment of neuroendocrine tumors, which got resistant after lutetium-labeled daughter date therapy. And another improvement is application of another form of somatostatin analogs. So far, we used an agonist of somatostatin analogs, but the antagonist of somatostatin analogs is also very effective. And in this report, they demonstrated good results of this lutetium-labeled antagonist, also actinium-labeled antagonist. So these are very promising. I really hope that such new radiopharmaceuticals will be approved for routine clinical practices. And another target of radioligand therapy is prostate cancer using PSMA ligand. PSMA is a molecule which is highly expressed on prostate cancer cells, and they conducted a clinical trial of using this lutetium-labeled PSMA 617, and this drug was approved by FDA in 2022, and nowadays this drug can be used in many countries. And also actinium-labeled PSMA ligand is very promising, and in this report, they demonstrated a good response of our prostate cancer, which became resistant after lutetium-labeled PSMA ligand. And there are some perspectives of radiopharmaceutical therapy. That is one radioligand would cover broader tumors. For example, using p-cadherin antibody, various spectrum tumors can be treated. And also using FAP ligand, that is a fibroblast activating protein inhibitor. This radiopharmaceutical also can cover a broader spectrum of tumors. And when we look at the good radionuclides, the production of radionuclides is our key issue. Especially, we think actinium-225 is very promising as alpha theranostics. The production of actinium-225 is really a challenge. There are several methods of production of actinium-225 using a generator or using nuclear aspiration or neutron capture or photon nuclear reaction and so on. And nowadays, very recently, a good production method of actinium has been demonstrated. It is the photonuclear production of medical radioisotope, which use electron linear accelerator, and that can really bombard gamma rays to target. And by this method, lutetium-177 or actinium-225 can be produced very efficiently, and I think this is a very promising method of radionuclide production. And also, astatine-211 is really a candidate alpha emitter for cancer therapy, in Fukushima Medical University after the nuclear disaster as a symbol of restoration from the disaster. They introduced a theranostics facility, and they have worked on the production of astatine-211, and the West Baltimore also visited this facility, and they are now doing researches, and some first-in-human studies have been conducted by using astatine-211. And astatine-211 has a short half-life of 7 hours, so we have to build a network of supply of astatine-211, and we have discussions on constructing such a network worldwide, the name of World Astatine Community. And at the end, I will talk about a little bit of clinical application of radiological protection. And dosimetry consideration is a good guide for when we work on development of new radiopharmaceutical, therapeutic radiopharmaceutical. And such a result can be incorporated in clinical guidelines, and by combining conventional pharmaceutical drug therapy. This is the example for such guidance for neuroendocrine tumors, and also for prostate cancer therapy with PSMA ligand. They conducted a dosimetric study, and absorbed dose in critical
1 minute.
organs can be demonstrated and incorporated in clinical guides. And the dosimetry for third party, including staff members of hospital, should be considered precisely. And at last, multidisciplinary cancer team for patient is critical, because it's all about patient-centered care. So our take-home message: we are currently witnessing a period of remarkably rapid progress in radiopharmaceutical therapies. A stable supply of radioisotope is essential. So, and the radiological protection, clinical guides, and multidisciplinary teams provide the foundation for radiopharmaceutical therapy. Thank you so much for your attention.
Thank you. Thank you, Dr. Makoto-san. Now we're going to be going to Dr. Fadi Jaira. He will be speaking about rationale and clinical utility of carbon ion radiation therapy. Dr. Fadi is a professor and chairman of the Department of Radiation Oncology at Oncology Institute of Cleveland Clinic, Abu Dhabi.
Good afternoon. Thank you for the invitation. Thank you, Muhammad, for the introduction. It's my pleasure to present today some review of the carbon ion radiation therapy, the background, rationale, and some clinical studies. Oh. Okay. I have no disclosures. This would be the outline of my presentations. I will review some clinical physics, characteristics of carbon ion, radiation biology, clinical studies, and I will end my talk on showing some of the future prospect and clinical trials. When we talk about carbon ion, we have at the clinicians to picture what we do today and what can be done with particle therapy. What we do today is on the left side. We treat most of our patients with X-rays or electrons. Of course, we all know that there is a proliferation of proton therapy facilities, and most of the particle therapy now in the world is delivered with protons. Carbon ion is the third on the right, with the size of the particle that can be used to treat cancer. Okay. So when we look at depth dose, in radiation therapy, the aim is to target the tumor. And tumors are located at different depths within the body of the patient. And we want to target the tumor. We need to know what dose can be delivered using photons. This is the first curve, photon beam. I don't know if you can read it from the back. Photons kind of like are attenuated through the body and reach the tumor at certain depth with certain dose. Now with particle, there is a different mechanism. You have a low entry dose, and at some point within the body, depending on energy and other things, you have what we call a Bragg peak. Everybody is familiar with Bragg peak, where the total energy of the beam is delivered in one shot, and you have no exit dose. And this is the most important feature of particle therapy that we are trying in clinical radiotherapy to take advantage of. Now, you can see that the peak, protons or carbon ion, is very narrow, but our physicists and engineers have been able to spread this peak to make it adapted to the depth and the size and location of the tumor, making the delivery of the radiation beam adapted to the tumor size and location. This is a very good engineering and very good tool to use in the clinic. Otherwise, it would be very difficult to treat with a very narrow beam. I'm sure you can picture that. Now, when we compare protons and carbon ion have lower entry dose, a steeper and narrower Bragg peak, and a steeper end, which means that the delivery of the energy is very steep and very quick compared to protons. Although both of them have the Bragg peak feature, the carbon ion is lower entry, steeper peak, and higher speed of deposit of energy. At the same time, because of this feature, the penumbra on the lateral sides of the beam is narrower. So all these things are favorable features for a carbon ion beam with less exit dose, sharper exit dose, or sharper deposit of energy, and lower penumbra, which means sharper edges of the beam and less collateral radiation. This is very important because we want in radiation therapy to treat the tumor and reduce the dose to surrounding tissues. So in summary, for clinical physics of carbon ion, it's a heavier particle, as you could tell, has a lowest or lower entry dose, sharper penumbra, a Bragg peak dosimetry with sharper and quicker release of energy, and steeper energy deposit. So this is some planning of radiation beams using either VMAT, which is what we use currently with our photons. In the middle is IMPT, or intensity modulated proton therapy. And the third one is IMIT, intensity modulated ion therapy, which is carbon ion. And you can just visually see the difference in the smearing of the dose and the incidental radiation around the tumor in the VMAT, IMPT, or IMIT, which is in favor of the heavy particle, which is the carbon ion. Radiation biology. With heavy particles, we have a high linear energy transfer, which means higher deionization throughout the radiation path of the beam. If you compare the linear LET of protons per keV per micrometer, is about 26.8, depending on matter, etc. But when you look at the carbon ion, is 24 or 25 times more powerful. This is what it looks like in reality. And this translates with higher LET, we all know this, with higher LET you have higher radiation biological effectiveness. So more ionization, more power, and more effectiveness biologically. Of course, RBE, I'm not gonna go into too much detail, but the RBE varies with the level of the LET. It goes like in this curve, it peaks about 100 keV per micrometer. So in summary, the RBE, or relative biological effectiveness of carbon ion, is much, much higher than other particles that we know in medical use. It depends on the cell type, dose per fraction, and there is no oxygen effect. In tumors, we have very, very frequently hypoxia, And hypoxia is actually leads to resistance because the effectiveness of radiation without oxygen is reduced. With the particle therapy of carbon ion, the effect of oxygenation is much less because it has more direct effect. And I will show you later. The Bragg peak depth, of course, and the biological endpoint determines the RBE, and it's tissue-specific. The less repair you have, which is typical in tumors compared to normal tissue, then the more RBE effect will take place, and the less cell kinetics, the slowly proliferating tissues, tumors that are very slow in dividing and growing are excellent candidate for carbon ion. Clinical studies. I know this is not a clinical meeting, but I want to share with you some of the clinical studies that have been produced, mainly in Japan, because most of the carbon ion technology and clinical studies have been produced by our colleagues in Japan. This is a very difficult site to treat. Pancreatic cancer, very, very difficult and very, very bad and poor results with conventional treatment. This is a study, small study published in 2017 by the J-Cross study. J-Cross in Japan, they have created the group of carbon ion user, and they have collected their experience into a registry trial, a registry study, and publish per site and present to the government the benefit of the carbon ion just for approval of indications. And this amount of scientific data is very valuable and very important for us to look at. So for pancreatic cancer that are locally advanced, non-operable, they treated them with carbon ion only, with or without chemotherapy. And you can see here on the left side, the survival is about 50% at 3 years. In operable pancreatic cancer, just to give you a comparative number, when we do surgery and chemotherapy and radiation therapy if needed, the survival at 5 years is 20%. Here, survival at 3 years, we don't have the 5 years yet, looks like it's plateauing, is 30%. Local recurrence is on the right side. And the use of chemotherapy was associated with even higher outcome, and the dose, there was a dose response. Even between 52 and 55, there was a dose response, indicating that if you give higher dose, and we know it from photon studies, we are now doing a lot of higher dose in pancreatic cancer with photons and seeing more results. So if you go with higher result, higher dose, you are able to produce better outcome. This is for head and neck, inoperable for the majority of the patients. T4 disease, 66%, 458 patients, melanoma, adenoid and squamous cell carcinoma, treated with carbon ion. This is the local control, very impressive for very extensive disease. And this is the list of patients included in those studies, about 80 to 100% local control, which is quite provocative for us as clinicians to see these numbers, because we never see these numbers with our conventional photon radiation. Of course, as our colleagues were learning how to use carbon ion, they were able to see some complications, and some of them could be very nasty. Grade 4 complications like visual impairment, optic neuropathy, and brain injury were present. About 6.6% of those patients had grade 4, which is very symptomatic complication from the treatment. Of course, the study started in 2003, and with time and with better imaging, better localization, better control of the treatment beam, I think these complications could be reduced. This is hepatocellular carcinoma, which is also another disease very difficult to treat, treatable by carbon ion with about 80% local control. And because of the localized beam and less radiation to the remaining part of the liver, you can treat patients who have recurrence for second times and sometimes third time. Rectal cancer, when it recurs, is very difficult to treat. Most of the time, we can't treat, or we can do exenteration. Those patients were offered carbon treatment in the J-Cross study, and they were able to enjoy or to have about 80% more local control. Of course, those patients die over time because they develop distant metastasis, but in terms of local control, it's quite impressive, with about 50% of patients remaining alive at 5 years. If you ask me about the outcome of recurrent rectal cancer, With conventional treatment, surgery, radiation, and chemotherapy, the results are much, much lower than that. Prostate cancer, this is another typical indication of carbon ion. 2,157 patients reported in this study. And the important observation here is that when you look at the outcome per risk category, those of you who are clinicians probably know that in prostate cancer we have low, intermediate, and high risk. And high risk is very difficult to treat. In this study, high-risk patients and low-risk patients, there was no difference if they were treated with carbon ion, indicating that if you put the dose with a good radiobiologic effectiveness of carbon ion, you can improve the outcome of high-risk patients. Chordoma, sacral chordoma 1, this is one of the last slides on clinical studies I will show you. Again, very impressive because most of those patients are difficult to operate because they are in a critically located region in the body, and you can't do surgery because you do more damage than anything else. So this study, 219 patients treated with 67 gray in 16 fractions. Look at the local control without any surgery, This is something that we cannot achieve with photon therapy. Of course, this is not very common disease. It's not every day we see this. But when every now and then we see those patients and we just can't do anything. If we have carbon ion, we can treat them, and with a reasonable, more than 60% local control. This is an example of a disease in the sacrum. The upper panel showing the disease, that shows you this is not operable. You cannot remove the sacrum of a patient. They cannot do that. And then when you treat with carbon ion, you have the outcome here. So one more study regarding second cancer, and we heard this earlier presentation about second cancers. There has some hint because of the less exit, less collateral radiation with carbon, you may reduce the incidental radiation of normal tissues and second cancer. And this is a clinical study from Japan also, showing in prostate cancer patients who had surgery or photons or carbon ion, and they looked...
You have 1 minute left.
Yeah. They compare it and they found improvement in second cancer over 10 years with carbon ion. Clinical trials, there are many clinical trials testing carbon ion with immunotherapy. This is very important. In the future, we will see a lot of those studies with immunotherapy because we we have data that with carbon ion you induce more immunogenicity in the tumors and you improve synergism between immune response and radiation. And FLASH, we just heard about FLASH. FLASH is usable and feasible with carbon ion, and this is some preclinical studies on FLASH showing the importance of reducing normal tissue effect and improvement metastasis-free survival. So this is something important to keep in mind. The technology is being reduced in size significantly, and with time, future, we will have multi-ion radiation with iron, with oxygen, and we can be able to do, with the technology, LET painting. LET painting with different ion, and just to finalize and to close, this is the system that we will be having at our center, hopefully in the future. Thank you for your attention.
Thank you very much, Dr. Gira. And now, as they say, now it's time for something completely different. We had a little space at the end of our session today, and I kind of took chairman's privilege and decided that I would like to ask my colleague, Yonsu Yeom, who is the recipient of the ICRP Bo Lindell Prize, to just tell us a little bit about some work he's doing that I personally find very interesting, and I hope you'll find very interesting too. It does help that I'm the chair of the task group that he's going to talk about, I think. But anyway, he's going to tell us a little bit about progress of TG113 on CT dose coefficients for pregnant women.
Okay, thank you. Thank you, Chairman. Kind introduction. Yeah, so this presentation is totally it's different field. It's not therapy but diagnostic area. But I'm really great to present, especially introduce the task group 113's work on CT dose coefficient for pregnant women. This is a really new study, and then I'm happy to introduce this one on behalf of our task group. So our task group, so why we are doing this work, I briefly introduce. So as you know, according to the ICRP, the report 160, as you can see, the effective dose, annual effective dose, about 50% is actually contributed by the medical exposure, this clearly indicates that why the the optimization of the medical exposure is important. And to do some dosimetry for the medical exposure, we have calculated the dose coefficient to convert the measurable quantity, for example, the X-ray imaging for DAP or CTDI, to the effective dose to the patient. So this coefficient have been calculated using the Monte Carlo simulation for the many years. However, there is no actually standard model methodology to estimate those coefficients for the medical exposure, and that's why there are many different approaches actually have been used depending on the institute or medical the hospital they use, and most national survey have used the stylized phantom as the basis of the calculation so far. And there are many different studies using different Boxer phantom as well. So there is an inconsistency to compare each institute. So for example, the NCRP 184, they estimated the survey, actually the CT effective dose for US populations, using the murder phantom, the calculated based on murder phantom, which is stylized phantom. And on the other hand, the UK PHE report, they survey CT effective dose for the UK population using the ICRP reference Boxer phantoms. So interestingly, UK effective dose tend to be higher than the US effective dose, CT effective dose, but the UK dose length products tend to be less than the US DRP. So that might be because of the inconsistency of the calculation. Maybe one of the parameters will be the phantom difference. So it's kind of the apple and orange comparison. So, and for many years, the ICRP has produced actually through the task group 136, the reference dose coefficient for diagnostic nuclear medicine. Those coefficients have been produced so far many years. However, as you can see, according to the UNSCARE report, the X-ray medical exposure is much dominant actually than the nuclear medicine exposure. However, the ICRP have never provided those coefficients for the X-ray, the medical exposure. So the ICRP task group 113 was established in 2019 to produce the reference, the organ dose and effective dose coefficient, the four common diagnostic, the X-ray imaging examination. So there are four tasks, major tasks, and in this presentation, I would like to introduce the pregnant female dosimetry for X-ray exposure. So this is the current membership of our task group. This task group is very big members here and really big project, I think. And so this task group is co-chaired by the Nina Patterson-Hans to represent the ICRP Committee 2, and also David Sutton also as co-chair to represent Committee 3. And also there are many experts and related to this field is also involved. So, so I just found this interesting, the study. They analyzed the trend in medical imaging during the pregnancy. And yes, so as you can see, the CT exposure during the pregnancy quite tend to increase over the past 20 years. And also the US and Canada also tend to increase. We can see that. So there are cases, exposure cases during pregnancy and even tend to increase, we can observe. And even radiography, we can see US, I think, tried to decrease, I think, but still similar level of over the 20 years. And the Canada, Ontario, they tend to a little bit increase even the radiography exposure. So city dose so we had the meeting in our task group meeting in the last year, and then we decided to kick off the patient dosimetry in our task group because our task group already complete the computation of the dose coefficient for radiography and also CT for adults and children. And also at the same time, the task group 103 already completed the development of pregnant the female reference mesh phantom. So it is really good time to start this new project. So maybe, yeah, already most of you saw this, the phantom, pregnant phantom, as you can see. So the task group 103 developed the mesh type, the reference of pregnant female phantom, including the 8 different gestational ages. And also this phantom have the male and female fetus very precisely modeled. So this is the maternal phantoms. You can see very detailed, how detailed model it is. And this is from 8 to 20 weeks, and this is a 25 and 38 gestational fetal weeks ages. And also, this is the fetal phantom, the rotational view. So you can see even the fetus is very small, but we try to the model very precise the organs in the fetus as much as possible. And also, in our task group already developed about the ICRP reference CT scanner, because most of the commercial CT scanners, the data is actually on disclosure. So it's actually we cannot distribute. So we decided to make the ICRP reference, the CT scanner that can be distributed, and also that represent the reference like a source condition. So we derive this reference scanner by averaging the dose profile from the 13 different commercial CT scanners. And then we consider the mass attenuation coefficient and also the density of the filter and to derive the dose profile. And then we convert to the thickness of profile of the multi-filter shape. So it looks like this. So to validate this ICRP reference CT scanner, we compare the effective dose, the calculated using the reference CT scanner with the effective dose calculated using the 13 different commercial CT scanner. So as you can see, the ICRP reference scanner quite provide effective dose in highly agreement with the average effective dose value among the 13 different commercial CT scanner. So I think we are good to go. So the calculation strategy basically is quite similar to what we have done for the adult and children. And so we're gonna calculate the dose coefficient per each beam slices, CT slice. So we're gonna provide the fetal organ dose, and also we will provide total body dose as well. And also we can calculate the maternal, the mother's organ dose. So we also plan to provide this maternal organ dose. And so in this calculation, main calculation we performed using the GENT4, the Monte Carlo code. And so this is the other condition. So for the computation simulation, we actually subdivided 2 parts. The step 1, each slice simulation, we use 10 to the 7 the particle. And then we try the second step to increase number of the particle, especially for the region of containing the fetus region, because fetus has a much smaller organ, so we would like to increase the statics, the calculations. So the primary calculation is have been conducted by in Yonsei University, mainly the mentee of this test group, Yumi Lee. She calculated a lot of this work. And also we are planning to do the spot check calculation for the independent calculation. So there are 4 members who volunteered for these spot check calculations. So this is the current status of the calculation result. As you can see, all the cases, step 1 calculation is actually complete. And now we are working on the step 2, the calculation. It takes much longer than step 1 because we increased the particle, but hopefully it will be finished this year. This is an example, the dose result. So we compare the mother's brain dose and also non-pregnant adult female dose in order to check the calculation is good or not. So at least when we look at the brain dose, as you can see, very good agreement with the non-pregnant female phantoms result. So because the head region actually is not the change during the pregnancy. So I think we indirectly confirm that our calculation is going well. And also lung, also generally good agreement, but you can see some difference there because the lung in this region a little bit the different when the pregnancy is getting older, is increased, and the lung is a little bit changed. So that's why some difference we can see, but generally we think it's good. And the other one is we also compare the fetus dose and also the uterus dose of the non-pregnant adult female phantom. We usually use the uterus dose to approximate the fetus. So as you can see in our calculation, we can calculate the fetus organ specific dose, and also fetal total body dose is also calculated. So when you look at, when you look at this, the uterus dose and fetal dose, you can see some quite difference. So it's anatomical change is really affect the dose difference. And this difference keep increase when we look at the older gestational ages, and you can see some difference more, and even the organ dose is much wide distribution we can see. So so the next step, as I said, I think the step 2, the calculation will be completed by this year. And then spot check calculation, we just start to initiate, and then it's gonna be complete, we expect early next year. And also we try to prepare and then submit the journal paper for this work in the middle of next year. And then after the finish, I forgot to mention here, but we also plan to implement the CT those coefficients into the web-based those calculator in the future. And then also next year we're gonna start radiography those coefficients for pregnant female phantom will start. Okay, I really appreciate again our task group members, and especially these members are really appreciate to help this work. Thank you.
Thank you very much, Yeon-Soo. And I'd also like to say special thanks to all of our presenters for keeping to time so well. We have some time for questions, so maybe we could ask, we have 5 minutes, so maybe we could ask our presenters to come and sit in the hot seats, and I'll see if we can So whilst they're doing that, does anybody have any, oh, we have a question immediately. Fabulous. Lady in white, I think. You may be in blue, actually, I can't tell what color you're in.
Yeah, that's right. Thank you, David. I have, first of all, thank you very much for these wonderful presentations. I have a couple of questions. The first one regarding the UNSCEAR risk of second cancer report. I might have missed that from your presentation. Did you do any subset study on the type of radiotherapy and the energy that was delivered?
Is this working? Yeah, very good. No, we did not. The problem with the very long latent period, we were really constrained to the early beginnings of radiotherapy. So most all the papers that were available for the meta-analysis were going to be first generation LINAC work. We were asked to revise to expand the report to talk about new therapies, carbon ion, proton therapy, radiopharmaceutical therapy. But the study, we had to rely on radiation epidemiology studies, and with 25-year latent periods, there just hadn't been enough time here. But you can infer that the second primary cancer risk would be lower simply because the doses are lower with things like moving from photon radiotherapy to carbon ion therapy. So those studies are now being done, and so I can envision in the next 5 to 10 years, UNSCEAR can come back to this issue, and we would have more studies on more modern radiotherapy techniques. So.
Yeah, fair enough. I was thinking also the differences in energy, for IMRT low versus high when you have the neutron dose as well for out-of-field irradiation. So,
I have to go back and look, but perhaps some of the early LINAC studies were above the gamma N thresholds, like 18 MV. So that's a good point.
Yeah.
That's a good point.
Thank you.
Thank you.
And my second question also relates to the risk of second cancer on carbon ions. I mean, it was a beautiful presentation. You showed all the physical and radiobiological advantages of carbons. However, I wonder, do we still have an issue with the carbon tail? The RBE, do we have enough data to know how much the RBE of the carbon tail is, and whether the Japanese study that I guess it was mainly a simulation showing that the risk of second cancer due to carbons is lower, actually in the future, in 10 years' time, we might find out that that's not really the case, because we are talking about low exit doses of carbons versus protons, but still the RBE, I expect it's high enough to cause normal tissue damage. Can you comment on that?
It's working, yeah. Very good question. I think this area is not fully explored. I think the study that I showed is a pure clinical study. It's not a simulation, it's a pure clinical study. Okay. They looked at prostate cancer patients in their institutions, and they compared second cancer over time, whether the patient was treated with surgery, so no radiation, photon radiation, or carbon ion. And carbon ion came lowest. I don't know why it's lower than surgery, but it came lowest, at least lower than photons. I agree with you with RBE. In carbon ion, there is uncertainty. And this uncertainty, as I tried to touch on, is dependent on so many variables, including the exit dose or the tail. But this is also true for protons. The uncertainty for proton is probably as much as for, not RBE, I'm talking about uncertainties in the tail or the deposit of energy. So I think the concept is, let's make it simple. In carbon ion, you have less, no exit dose and no lateral radiation because of the sharp penumbra. Yep. So this, per se, may reduce the incidence of low dose in the vicinity. Now, is this demonstrable? We can demonstrate it and model it, I don't know. The study is only one study. I've seen another study coming out showing no difference between photon and carbon ion. But in general, and I will close here, for protons, we use it a lot for pediatric because we want to avoid second cancer and exit dose. And this is actually, in principle, is very attractive, and everybody believes in it.
Okay, thank you.
Do we have any further questions? Lady over here.
Thank you. It's not a question, it's out of curiosity, and this is to Dr. Fadi. So the physics characteristic of the ion beam therapy, the depth dose distribution, the LET, all that makes it a very good therapy tool for pancreatic cancer, as you mentioned. So you showed us the result of one study. I was hoping to see a better progress than just 30%. And you only showed us one study. Was it only one study? And it was published on 2017. So was there any limitation in this study that made others not pursue further, particularly for pancreatic cancer? Thank you.
For what cancer, sorry?
Pancreatic cancer.
Oh, okay, very important. The limited number is based on the fact that centers are mainly, of carbon ion, are mainly present in Japan. Japan has more than half of the carbon ion centers in the world. And they have started slowly to regroup and collect their data. And pancreatic cancer, I mean, we have to put ourselves in the shoes of our colleagues in Japan. So they didn't know that carbon ion would be extremely useful for pancreas until they study it. So every study they've done, they've actually started with small steps. They had to provide, first of all, background and rationale to do it, and also safety to do it. This is all takes time. In my opinion, that would explain the low number of patients. I can tell you that because of this data, everybody in the world now is looking at carbon ion as a game changer for pancreatic cancer. In Korea now, there is a trial going on to test comparing standard management of pancreatic cancer, which is surgery, chemo, etc., versus carbon ion because of this preliminary data from Japan. So this is actually hypothesis-generating studies that are very essential and very useful for us to build on and continue the research.
Thank you, Dr.
Thank you very much. I think I have to call proceedings to a halt. It's very interesting. I had some questions for our panel as well, but I'm guessing that it says time is up and people are starting to go and everyone wants their coffee. So thanks again. Thank you to our excellent presenters for a series of fine talks, and I'm sure we'd all like to say thank you to them. And with that, we'll see you next time.
it's already time to start. Good afternoon, everybody. It's time to open this session of Medical 3. We will handle for occupational exposure in medicine. I think that our topics of occupational exposure in medicine, they are critical when we look at the patient-centered care. And so I will introduce our reporter of our session, and the name is Alexander Mediadovsky. He is our ICRP Task Group 116 mentee, and he has a great effort to wrapping up the poster presentation. So, Alexander, the floor is yours.
Thank you for introduction. So, good afternoon, and I will present briefly an overview of session 15. This session brings together posters and pre-recorded videos from different regions and discipline. So, in total, the session includes 18 contributions from 12 countries, and with strong participation from Middle East, Europe, and Asia. There are 16 posters and 2 videos. To better understand focus of these studies, keywords provided by author was analyzed. As we can see, radiation protection dominates, and followed by clusters of interventional radiology, nuclear medicine, diagnostic radiology, and occupational radiation dose. Others keywords appear once, and I believe that it shows that topics are very diverse. So, all topics were grouped in different categories. There are 4 categories, and first one is epidemiology and occupational risk. This group of studies addressed health risks in radiation workers. This ranged from long-term cohort studies in X-ray workers to monitoring of air crews and industrial workers, and to evaluation of clinical personnel. The common thread here is quantifying occupational risks and understanding those response relationships. So, the next one is this group of focuses on those constraints and monitoring. The several studies propose those constraints for medical and industrial workers. Introduce a national dose register system, and also test new feedback tools, including automated emails notification system, and improved use of protection gear. So, the next group about radiation protection equipment, several posters and videos addressed practical aspects of radiation protection. This included verification tools for shielding, studying of the effectiveness and durability of lead-prone, and also comparison of protective methods in nuclear medicine, and role-based assessment for interventional radiology staff. And Finnish group of posters, there are studies on protection in the alpha therapy, neutral detection and monitoring in proton therapy, and also GPT-based interactive tools for radiation education. So, this shows how innovation is already shaping the modern occupied occupational radiation protection. So, And thank you for your attention. All posters and videos are available on the official portal, ICRP portal, and I highly recommend to check it and look at it. So thank you.
Oh, thank you very much, Alexander. I really respect for your effort of wrapping up many posters. Thank you so much, Upload again. And before move on to our speaker, I will introduce ourselves. Cheers. Dr. Hassan Karita from Qatar, and I'm Makoto Hosono from Japan. So I hand it Karita.
Thank you very much, Professor. And our next speaker from WHO, Dr. Farid Shanoun. He's got experience 27 years in radiation protection, 4 years in WHO, 9 years in UNSCARE, and about a few years in the Ministry of Health in Luxembourg. And he will be talking to us about radiation protection in the context of an integrated approach to occupational health and safety. Dr. Shanoun, the floor is yours. Thank you.
Thank you, Dr. Hassan and Dr. Makoto-san, for inviting WHO to this session to present our work on occupational health. This presentation is prepared together with our unit head, Dr. Emily van Deventer, who sends her regards and apologies for not being here. Just let me see this. Yeah. So, as stated in our constitution, WHO constitution, health is the state of complete. Sorry, I cannot see the slide, so I need either to look here or here. It's okay? Yeah, okay. Health is the state of complete physical, mental, and social well-being, and not merely the absence of diseases or infirmity. And our objectives at WHO is the attainment by all people of the highest possible level of health. We have been working for a very long time with our sister agency, the ILO, to implement one of our core functions, namely to act as the directing and coordinating authority on international health work. As you might know, the World Health Assembly recently approved the new global program of work for WHO, which is called GP14. However, due to the major challenges in WHO facing at the moment, there are some consideration on how to implement this ambitious program and goal to promote, provide, and protect health and well-being of everyone everywhere. As mentioned before, a core function of WHO is monitoring the health situation and assessing health trends, including occupational health exposed persons. You can see public health refers to the health of the population as a whole, considering all stages of life from pregnancy to senescence. Occupational health is an area of work in public health to promote and maintain the highest degree of physical, mental, and social well-being of all workers in all occupations. Already in 1950, WHO and ILO established the Joint Committee on Occupational Health with the following objectives: promoting worker health, improving workers' working conditions, developing organizational, cultural, and prioritize health and safety, integrating occupational health into public health, supporting national policies and action plans, and collaborating across disciplines and sectors. In 2007, the World Health Assembly in Resolution 6026 endorsed the Global Plan of Action on Workers' Health to provide the political framework for development of policies, infrastructure, technologies, and partnerships for achieving a basic level of workplace health protection by all, at the moment, 194 member states of WHO. A few years ago, two UN General Assembly resolutions or declarations on the prevention of and control of non-communicable diseases and on universal health coverage address the fact that a third of the world's population is working. And with over 2 million preventable work-related deaths occurring annually, occupational health must be a shared priority for and among us, the international organizations. How we do this? WHO is working with different partners at different levels on the topic of occupational radiation protection. Besides ICRP, where we are today, and ICNAP, the International Commission on Non-Ionizing Radiation Protection, we work with ICO, the International Commission on Occupational Health, another very important NGO in official relation with WHO. Further, and you have seen in some slides, we are working closely with the IEA and ILO on this topic. I will give later a very specific or practical example of others' cooperation. And last but not least, we have over 20 collaborating centers with WHO dealing with radiation and over 30 with occupational health, and all contribute to the implementation of the WHO program of work. ICRP's recommendations pioneered occupational radiation protection, and the International Basic Safety Standards represents the international benchmark for radiation safety. An entire section on the BSS address occupational exposure and safety requirements for workers. WHO, as a co-sponsor of the BSS, has been supporting member states in implementing these requirements, including those related to worker health. WHO produced a number of relevant and important occupational health publications linked to radiation, such as the Guide for the Development and Implementation of Occupational Health and Safety Programs for Health Workers, which was published together with the ILO in 2022. This guide is complemented by a WHO e-tool for prevention and control of occupational hazards in the health sector. The guide includes a section on preventing exposure to radiation in healthcare settings, which now I will go not through all the details because you are the radiation protection experts, but I would like to highlight in the guide some key elements of occupational health and safety programs. And they are written policies, education and training, risk assessment, incidents reporting, and compensation. These all are elements which you know from your radiation protection context, but also are applicable to other occupational health in general. Another online training source are a module for responders, responder well-being and ethics in emergency preparedness and response, and the WHO course on occupational health and safety, which was developed in the context of COVID-19. Both are free and online available. WHO's work on health or occupational health is part of an integrated approach also linked to patient safety as formulated in WHO Global Patient Safety Action Plan, which requests to inspire, educate, skill, and protect workers. Before concluding, I would like to highlight or mention the important cooperation I mentioned before, or activity with the IEA and ILO, namely the update of the IEA Safety Report number 5 on health surveillance of persons occupationally exposed to ionizing radiation, a guidance for occupational physicians. The IEA kindly organized a first consultancy this February in Vienna, and the drafting and reviewing of this document is ongoing. As a co-sponsor of the BSS, WHO has been supporting member states in the implementation of its requirements, including those related to worker health. For example, requirement 25 on health surveillance and requirement 28 on special arrangements for female workers and persons under 18 years, which will be addressed in the updated safety report. Let me conclude. Occupational health is an area of public health to promote and maintain the highest degree of physical, mental, and social well-being of workers in all occupations. Radiation protection of workers is essential and should be based on the 3 radiation protection fundamental principles: justification, optimization, and dose limitation. Pregnant workers or pregnant health workers at risk of radiation exposure should be provided with information on the risk to the embryo, fetus, and breastfeed infant. Medical surveillance prior to an assignment, periodically, and at the end of an assignment or before reassignment to another role, as well as monitoring occupation dose, are crucial in occupational health. Maybe last but not least, international cooperation in radiation protection at work promote the safety and health of workers worldwide. Let me thank my colleague and friend, Dr. Ivan Ivanov from WHO, whose slides served as a fundament for this presentation, and Dr. Shengli Niu from ILO and Dr. Ji Zheng Ma from the IEA, who both provided the information on the joint safety report. Finally, please allow me to encourage you to attend the International Conference on Radiation Protection in Medicine, organized by the IEA and co-sponsored by PAHO and WHO, and which will be held in Vienna this December. It might be the right place to further engage on occupational radiation protection and health matters. Thank you.
Thank you very much, Dr. Farid. I think we have Shangli from ILO. He's supposed to have been a speaker tonight, but for some reason he couldn't attend. So we have at the end of the session some time for question and answer. So we'll leave the question and answer to everyone to the Q and answer session because we have more time than expected. Thank you very much, Dr. Farid. And I just want to ask if Ms. Khulud Al-Siraj from Saudi Arabia, yeah, okay, good. So thank you very much, welcome.
Thank you very much. And thank you, Farid. And we will move on to next talk. I will introduce Dr. Hiroko Kitamura from QST Japan. And the title of her talk today is the towards effective and rational radiation health surveillance, nationwide survey of occupational health institutions in Japan. Dr. Kitamura, the floor is yours.
Thank you for your kind introduction, Professor Hosono. Good afternoon, everyone. My name is Hiroko Kitamura. I'm honored to present on behalf of our team at the National Institute for Quantum Science and Technology in collaboration with the University of Occupational and Environmental Health, Japan. Today, I'd like to share findings from a nationwide survey on radiation health surveillance in Japan. It's green one. Thank you very much. Here is a brief outline of today's presentation. I will talk about the introduction, methods, and the discussion, the conclusion. Before diving into the survey itself, let me briefly explain the legal framework of radiation health examination in Japan. Under Article 66 of the Industrial Safety and Health Act, employers are required to conduct general health examinations for all workers and special health examinations for those engaged in hazardous tasks. Radiation workers are required to undergo both types of health examinations. Special health examinations are mandated for workers exposed to special health hazards such as organic solvents, lead, ionized radiation, and so on. The special health examinations are designed to detect early signs of health effects related to exposed specific hazards. The immediate goal is to enable early intervention and support continuous health maintenance. More broadly, these examinations reflect the core aim of the Industrial Safety Health Act to protect workers' safe and health and promote their well-being. This slide shows the contents of the radiation health examination. According to Article 56 of the Ordinance on Prevention of Ionized Radiation Hazards, employers are required to assess radiation exposure history and perform the following medical tests: a white blood cell count and differential, a red blood cell count and either hemoglobin or hematocrit, an eye examination for cataracts, and a skin examination. Although the legal framework clearly defines the required items for radiation health examinations, the way these examinations are implemented in practice remains unclear. So our study aims to describe current practices, identify challenges, and explore variations in how these examinations are conducted. We also sought to assess how closely these practices align with the intended objectives of the special health examinations. Let me now turn to the methods. We conducted a cross-sectional web-based survey to explore how radiation health examinations are currently being implemented across Japan. Our target population included all 173 occupational health institutions affiliated with the National Federation of Industrial Health Organization, known as ZEN-EIREN in Japanese. These institutions primarily provide occupational health services. The survey was conducted in January 2025. As shown on the map, occupational health institutions are distributed across the country, reflecting a broad range of regional contexts and operational settings. And this slide shows the key domains of our questionnaire. We asked the institutions about how they conduct the legal mandated radiation health examinations, including how they assess radiation exposure history, how they perform eye examination and skin examinations. On the other hand, we did not include questionnaires about laboratory methods for blood tests because ZEN-EIREN member institutions conduct internal quality control, participate in external quality assurance, and many have undergone a comprehensive performance evaluation. So we believe that the laboratory analytical methods are standardized. So move to the results. We invited 173 occupational health institutions to participate in the survey and received response from 90, giving us a response rate of 52%. Among these, 89 institutions reported that they conduct radiation health examinations. We then asked how they assess workers' exposure history. Over half, 52.8%, reported relying primarily on self-reporting by the workers themselves. A smaller proportion received dose or work information from employers, and about 1/4 indicated that the assessment was done entirely by the employer without institution involvement. Next, we looked at how institutions conduct eye and skin examinations. For eye examinations, the most common method was visual inspection, used by about 60% of institutions. And pen light examinations were used by nearly 30%, while slit lamp examinations and other techniques were rare. For skin examinations, almost all institutions relied on visual inspection. Techniques such as dermoscopy or derm camera were not reported. And this slide shows the coverage of radiation health examinations conducted by the member institutions in fiscal year 2023. Nationwide, approximately 379,000 radiation health examinations were conducted. Of these, the member institutions conducted for about 157,000 examinations, representing 41.6% of the total. And this slide shows the roadmap for the discussion. I will talk about coverage and representativeness, exposure history, eye and skin examinations, feasible improvements with Article 56, and reflection and path forwards. Now, let's begin the discussion by coverage and representativeness. Taken together, the findings presented here suggest that the results of this survey likely reflect a substantial share of the current state of radiation health examinations in Japan. Although non-response bias and provider volume bias may be present, and the data does not represent the complete picture, we believe our results provide meaningful insights. Let's now turn to how exposure history is assessed. As shown here, only 11.2% of institutions obtain those records directly from employers. Without those records, it may be difficult to confirm exposure history, and medical findings should be interpreted with caution. As feasible improvements, institutions could attempt to obtain those records using passbooks or e-systems. They might also consider using structured checklists to gather information about tasks and environments. And in case where only self-report is available, flagging these for follow-up may help ensure appropriate interpretation and care. Regarding eye examinations, most institutions rely on visual inspection and only pen light examination. Slit lamp examinations feature the standard for lens evaluation were reported in only 2% of cases. Retro illumination cameras, which can detect posterior subcapsular changes without dilation and are well suited for radiation cataract screening, were not used at all. These examinations are typically undocumented beyond written notes. Without imaging, findings cannot be verified or reviewed later. Posterior subcapsular lens opacities, often asymptomatic in early stages, cannot be reliably detected by visual inspection alone. referral criteria to the ophthalmologist are unclear, especially for asymptomatic cases. Without documentation or structured referral logic, subtle radiation-related changes may be missed. With regard to skin examination, nearly all institutions rely solely on visual inspection. For example, dermoscopy, widely used in dermatology, combines magnification and lightening to enhance detection. So, visual-only examination may miss subtle findings. And currently, no comprehensive photo atlas of early radiation-related skin changes is available in Japan, so many examiners may not be familiar with what to look for and may lack visual references. And in routine health checkups, skin observation time is often limited, not due to examiner intent, but due to systemic constraints. These include institution scheduling, the need to avoid long waiting time for examinees, and pressure minimizing time away from work. So let's now consider feasible improvement within the framework of Article 56. For eye examination, referral thresholds can be guided by structured matrices, such as the examples shown here, right side of the slides. Introducing street lamp and supporting examiner training may also enhance sensitivity. And for skin examination, improving examiner training may also enhance sensitivity. For skin examination, improvement could include clarifying referral criteria based on findings and job context, allow photo documentation, and supporting examiner training. Dermoscopy use may help improve detection. And finally, I'd like to offer some reflections and possible paths forward. To improve the effectiveness of health examinations, additional resources may be needed, such as examiner training, diagnostic equipment, and sufficient time for each examinee. These are not minor adjustments, and they place real burden on employers and occupational health institutions. It may be worth asking whether uniform procedure-based examinations for all workers are truly efficient, especially when exposure levels vary widely. A shift toward risk-based surveillance could allow examination content to reflect individual exposure dose. To achieve this, accurate and continuous exposure monitoring must be available for all workers. Bridging the gap between regulation and practice will require. It means integrating diagnostic advances and ensure quality across the entire health examination process, including information flow, procedure training, appropriate testing, and coordination among stakeholders. In summary, the nationwide survey shows a heavy reliance on self-reporting for exposure history and basic method for eye and skin examinations under Article 56. With substantial but incomplete representativeness, these findings reflect much of current practice in Japan. There are steps we can take now within the framework of Article 56, trying to retrieve those data and defining referral criteria for ophthalmologists and dermatologists. Looking ahead, we may consider moving toward risk-based surveillance where examination content is tailored to individual exposure dose. These steps may help us build a health surveillance system that is not only compliant, but also meaningful, responsible, and sustainable. That's all for my presentation. Thank you for listening.
Thank you, Dr. Kitamura, for your very interesting talk, and we will receive questions after all talks. Thank you again, Kitamura. Applaud. Well, we will move on to next talk. I will introduce Dr. Hulud Al-Zilaj. She is from NRRC, Saudi Arabia. And the title of her talk today is Occupational Radiation Protection and Health Surveillance of Exposed Medical Workers in Saudi Arabia. Dr. Al-Siraji, the floor is yours.
Okay, thank you. Hello, everyone. My name is Khulud Al-Siraj. I'm the Director of Medical Practices at NRRC. Today, I will present an overview of occupational radiation protection and health surveillance for medical workers in Saudi Arabia. In this presentation, I will start with an introduction, then highlight the NRRC regulatory frameworks, key requirements, and the achievements, and finally, further directions. My goal is to show how the NRRC ensured the safety of medical workers exposed to radiation. Medical workers in diagnostic and interventional radiology, nuclear medicine, and radiotherapy are occupationally exposed to radiation. Therefore, effective radiation protection and health surveillance are essential. The NRRC has developed a strong regulatory framework to protect these workers and to ensure compliance. The NRRC framework is comprehensive. It combines clear requirement, national system, and continuous oversight. All of these can be achieved through establishing regulations, establishing safety guides, such as NRRC R01 Radiation Safety Regulation, and also a safety guide such as the SG20 Guided for Radiation Protection Development. It also can be done through operating the National Dose Registry, which collects and analyzes dose records to track exposure trends. And we obligate all licensees to conduct pre-employment and periodical medical examination for exposed workers with focus on those at high risks. In addition, we in the NRRC ensure radiation workers received education, training, and continuous awarenesses program or radiation risk and protective practices. And we obligate to update the licensee to update the dose constraint, and we also, as NRRC, update our regulatory guidance tool for more optimization. Medical facilities must be comply with several key requirements. So all facilities must be licensed or registered before operation. They shall implement radiation protection program, RPP, in accordance with the NRRC requirements. They shall establish quality assurance program and follow NRRC specific regulation, monitoring of workers. They shall also provide dosimetry services to all exposed workers. All facilities must establish a specific dose constraint tolerated to the radiological practice and maintain dose and medical records for at least 30 years post-employment. I would like to emphasize that compliance is not optional. It is a legal obligation to protect our workers. As specified under NRC R01, licensee shall ensure that occupational exposure are kept ALARA, as low as reasonably achievable, considering economic and social factors. Also, they shall provide workers with suitable personal protective equipment and ensure individual monitoring of occupational exposure. Licensee shall promote radiation protection, training, education, and awarenesses among all occupationally exposed workers. Dose constraint is not a legal limit, but it's a planning tool used to keep exposure below regulatory limits. Each facility sets its own dose constraint depending on workload, shielding, and work conditions, and the NRC reviews and approves these dose constraints accordingly. As we all know, monitoring enables early intervention and prevention of long-term health risks such as cataracts, cancer, and genetic effects. And it's a cornerstone of occupational radiation protection. Therefore, NRC established a national registry to monitor radiation exposure for all workers in the kingdom. And each worker has an electronic file to track cumulative dose. The NRC's national registry collects and analyzes these data, providing annual dose reports and flagging any overexposures. This system enables quick prevention action and national analysis to promote a culture of safety. In 2023, occupational dose records covering a period from 2018 to 2022 were collected and monitored for a total of 4,000 medical workers around the kingdom. And we set dose constraints at that time for each practice as following. For interventional radiology workers, the dose constraint was around 4 millisievert per year. For diagnostic radiology, it was 2 millisievert per year. For nuclear medicine, it was 2 millisievert per year as well. And for radiotherapy, it was 1.5 millisievert per year. As part of strengthening regulatory control and ensure alignment with national safety regulations, dose constraints were established. Following 2 years of implementing radiation protection strategies, routine radiation exposure monitoring, and the activation of National Dose Registry, in 2025, this optimization has led to a measurable reduction in occupational exposure over the years. So the dose constraints were revised and lowered. Here we can see the average occupational doses across medical practices. As I mentioned in the previous slide, in 2025, those constraints were higher a little bit in some practices, such as in interventional radiology. And as we can see, this year, we recognize that the dose constraint has been lowered to 2.2 millisievert. Also for diagnostic radiology, dose constraint has been lowered to 1.5 millisievert per year. And as we can all see also, all are well below the national dose limits. And the readings above constraints are investigated immediately, ensuring ongoing compliance and safety. Also in this slide, we can see the nuclear medicine and radiotherapy. Dose constraint in nuclear medicine was 2 millisievert by 2022. And the last study we did, dose constraint now is 1.7 millisievert per year. Health surveillance ensures medical workers are fit for duty and remain healthy over time. Pre-employment and periodical medical exams are mandatory at least every 3 years. If a dose limit is exceeded, Special health surveillance must be performed. All of these requirements are stated clearly under NRC R01, Section 55 and Section 56. The NRC has established a solid national framework, maintained low occupational dose, improved safety culture, and strengthened health surveillance system. These achievements reflect our commitment to protect medical workers across the kingdom. Looking ahead, the NRC aims to integrate real-time dosimetry with the health system expanding medical checks to all radiation workers, enhance data analytics, and conduct long-term epidemiological studies. These steps will further strengthen evidence-based regulation. In conclusion, the NRC has successfully combined technical oversight, monitoring, and health surveillance. The NRC continues to strengthen regulatory oversight, close monitoring gaps, and promote culture of radiation protection. These actions not only improve compliance, but also ensure suitable protection for all radiation workers and support policy development in Saudi Arabia. And at the end, please allow me to express my sincere appreciation to my colleague, Ms. Mathal Al-Jaed, and all my team in Medical Practices Department for their valuable contribution, collaboration, and support throughout this work. And to contact us, please send us an email at the emails here. Thank you so much.
Thank you very much, Dr. Lucilaji, for your very important talk. And we will have a question after the last talk.
Thank you very much. Our next speaker from Oman, Naeem Al-Maimani. She's a senior medical physicist with master's degree in medical physics, and she's got the International Medical Physics Certification Board, and she worked at Sultan Qaboos Comprehensive Cancer Care and Research Center in the Radiology and Nuclear Medicine Department. Dr. Maimani, the floor is yours. Thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. Dr. Hassan, thank you for the introduction. I know it's the ending of the day, but I promise I will be very brief and short. So in my talk, I will start with background and objectives. Then I will move to study design and methods, results and discussion, and finally the conclusion. So as all we are aware that intervention radiology involves high exposure to the staff, which is a result of scatter from patient and a partial from the primary beam. Staff roles involving interventionists, nurses, and technologists, they are experiencing different exposure levels, definitely related to their roles during the procedures. And by accurate assessment of their practice, we can help them in optimization and provide good technique for radiation protection. At Sultan Qaboos Cancer Center, these are the most frequent procedures performed. The highest number accounts for the port catheter insertion and followed by the central vein catheterizations. Of course, most of the procedures are related to the oncology patients. The staff involved in IR suites, we have 2 interventionists, 4 nurses, and 3 technologists. The aim of this study, we decided to evaluate the occupational exposure received by IR staff, to reveal the doses, and then improve the practice where it is needed. So it's a retrospective study. done at the Sultan Qaboos Cancer Center, Department of Radiology and Nuclear Medicine. The participant, all IR staff. So we started by collecting radiation doses for all the staff. The dose monitoring system followed at Sultan Qaboos Cancer Center. We are monitoring the whole body doses using TLDs, which was one under the aprons, ring dosimeters that provided for nurses and interventionists, I-bands, dosimeters, and personal dosimeters, which was one over aprons. The personal dosimeters, actually, they are real-time monitoring system, measuring the scattered X-ray radiations, and it is, as I said, is one over aprons. So it showed the cumulative dose and the instantaneous dose for each step in microsievert and during procedures time. Then the readings can be extracted, and we can get those reports for each staff per month, as it's shown in the figure. Then we decided to collect the dose report from the active dosimeters and do tracing the procedures and correlation with the patient dose metrics. This is including the dose area product, or DAB, air kerma at the reference point, and fluoroscopy time by using the dose management system. Moving to the results. What we have collected from the TLDs, HP10 rings and I-band. So the table is showing here the total effective dose received by each staff categories. So for the 3 types, all they received less than 1.01 millisievert, which is the minimum reportable dose at our system. For hand, the highest reading recorded by nurses, as shown there, they got around 5 millisievert per year. For I-bands, the highest recorded by the interventionist, which is around 3.4 millisievert. So looking to the readings, the trend is clear. More close to the beam or patient, higher scatter radiation, so higher exposure will be received by staff. For the technologists, the readings were not significant because usually the technologists are far away from the primary beam, and they are most of the time with the console when they are monitoring the exposures, in compared to interventionists and nurses. For the active dosimeters, so the highest reading, the cumulative dose in millisievert per year received by the nurses, followed technologists and then interventionists. So looking to the results here, we can see that the trend is a bit shifted. For nurses, as I said, they are close to the patient and the primary beam, so they are receiving high exposures. But the interventionists, when we exported the data, we noticed that most of the time the readings were 0, so they were not wearing the active dosimeters while they are performing their procedures. We collected the active reports, and then we tried to reveal the data with dose management system. So we used nurses' report, actually 3 nurses. We tried to trace where they received high exposures, and then we trace it in dose management system. So the 3 nurses, they did agree that they got high readings during these procedures. With embolization pulmonary, we found 1 case, and you can see the total air kerma was very high, and the procedure is almost one hour. And also for the radioembolization, radiofrequency ablation, and the mapping also procedures. So it's showing us this is the most complicated procedures done with the oncology patient, and for the fluoroscopy time is quite long. This is the end. In conclusion, I would say that the occupational exposure at our center still within the limit, but they are meaningful, especially for interventionists and nurses. The results highlight two risks: the total workload that covered by nurses, and the procedure complexity and the proximity. We can say that leaded glass and thyroid aprons are important, and also using shielding during procedures also is essential in order to for protection. Routine monitoring for eye, thyroid collar, or whole body also is important. In my country, we have a limitation in providing the eye bands and rings, so or not all staff they got. And this finding can support us to justify our request to the ministry. Finally, real-time monitoring dosimeters. They can quantify dose, not only that, but also they can show us when and where the high exposure that happened, so we can trace back and we can help in optimization. Also, these dosimeters, they can show the color, the dose level with the color, so they can manage during the procedure using shielding or divide the workload between them. That's all, and thank you for your attention.
Thank you very much, Dr. Naima. May I ask the speaker to come up to the stage? I hope Dr. Siraj is still around, or? Yeah. So just to say, it's very interesting talks, starting from comprehensive approach to health, to occupational health, and we had a national survey about occupational health center in Japan, and the occupational health and safety program and health surveillance for people working in medical field, and finally the interventional staff, those in Oman. So I'll open the floor for question. We have enough time for any question, please. If anyone have any burning question, please. Yes, the front row.
Thank you for because of 2 years later, by the 1st of 2025, we collect all the dosimetry reports for all workers from 2022, or let's say 2023 and 2024, 2 years after implementing the regulations and licensed many facilities and raising the awarenesses. And then we found out that the dose constraint has been lowered.
So the overall dose for your cohort came down?
Yes.
Right.
Yes.
So did you confirm that everything was the same in terms of wearing the TLD, where they wear it, above, below the apron, etc.? All that was the same, or there was a change even in the way they use or apply
this is part of the regulatory function. Like, actually, we're not only licensing them, we go and do inspection. And through the inspection, we found like mistakes, we guide them to the right things, we enforce them to follow up the requirements by the NRC. So many different things come together to make this a reduction.
This is great.
Yes.
This is wonderful, and we'd like to learn from your experience.
Yeah, sure.
You know, to jump from 4 to 2, that's a big jump.
Sure.
And
Yes.
it's the
Yes.
entire cohort. So what was the main
I would like to add something
improved?
that many of them wasn't under regulatory, or like wasn't under the NRC regulatory. That's why they were like not under control, let's say. So once they are under NRC control, they follow up the requirements, they know that there is a regulatory body, so they're strict with the requirements more and much better than before.
So based on your experience, what would you consider the one thing that has drifted and changed the dose spectrum and make it down? What was the one thing that changed? What do you think? From the practice, I mean.
I can say the licensing, the authorization process, the putting them under control. We have inspection all the time of the licensing. We have regulatory inspection. We do it. Also the awarenesses. We are in each events. We are there. We are trying to reach to those workers, show them the issues and how they can be with the low doses, how they can be restricted with the NRC requirement.
Thank you.
Thank you. I have another question, if you don't mind, and it's to Ms. Naima. So I just wanted to ask, you use two types of dosimetries.
Yes.
So a passive and an active. So what was the uncertainty, the error in both? Because I see with the active, there was a change of trend. So instead of interventional physician receiving the highest, the nurse now is showing the highest.
Just bear in your mind that the active one was not replacing the TLDs. It's just for the practice management.
Yeah, I understand.
So it's not added to the effective.
I understand.
Yeah.
But what makes the trend change could be associated with the uncertainty, the errors of the reading.
But it's only local challenges. So for nationwide challenges is to improve our systems to record workers' radiation doses and to increase our institutions to perform health examinations and introduce training times for examinees to use more useful and more sensitive equipment to train for examiners, I think.
Yeah, I fully agree. Education and training is an essential matter, and also an improvement of the system itself is critical. By the way, for our examination of equivalent dose of skin and dose, do you think ophthalmologists and dermatologists are cooperative to do such inspection among workplaces? Do you have any idea about that?
I think if many dermatologists can go workplace and conduct health examination, it's very nice, but dermatologists are very busy and they don't want to go to workplace and conduct health examination. So I think we will develop equipment to take photos of our skin, workers' skin or nails, and centralize the pictures and judgment or implementation is centralized system will be support our health examination, I think.
You're talking about some remote diagnosis of
yes,
skin.
Yes.
Yeah, that is very interesting. Do you have any specific plan of doing such a remote diagnosis for that purpose?
No, I guess it is my idea.
But it's really interesting. Thank you so much. And I have another question for Alcilage. And you talked about a registry of those workers, and during such registry, I think there are workers who moving from one workplace to another. By your registry system, is it possible to track such workers?
Yes. We actually go with the national ID, or we call it Iqama ID. So even if they are not a national worker, and this ID is the ID is like forever with the worker. So that's how the registry collect their doses. It's not depending only for the hospital he work or the place he work on it.
Yeah, that's
so
very
we
good.
can track all places.
And again, back to those constraints, my understanding is that those constraints is different from workplace to workplace.
Yes.
But you have a tracking system by registry. So how do you handle those constraints and those tracking system?
Yes. Actually, within our tracking system, we set the dose constraint that I show you. It's just for us as a tool to verify and to analyze their data. But we enforce each facility to establish their own dose constraint based on their workload, based on all the parameters related to the practice they have, and we review and approve them through the authorization process. So once any workers achieve or exceed the dose constraint we set, we go through the file of the hospital. We make sure that if he or she within the dose constraint established by the facility or not, and then we investigate more and know what's going on. Yeah.
It's really a good way of managing those for all workers moving around. Thank you so much.
You are welcome.
And I have another question for Dr. Marnie, and it's about interventional radiologist. When you talk about interventional radiologist, you do not include cardiologists, neurosurgeons. Am I right in understanding this? And do you?
Yes, I did include because there are no procedures done under our department. It is oncology, and I showed the procedures.
Oh, I see.
Yes, so there is no cardiology and no neurology.
Oh, I understand the situation.
Yes.
Yeah, because usually our cardiologists and the neurosurgeons who use fluoroscopy may receive a larger dose as compared to interventional radiologists.
Yes.
So
Actually,
I was so curious.
Yeah, our center is nearby the Sultan Qaboos University Hospital, and they do have emergency cardiology cath lab, and they do these procedures. So, which is needed, they are transferred to the other hospital.
Great, thanks.
Thank you.
Thank you. You like to close? Yeah, thank you very much for the panelists. It's been interesting talks and discussion, and I would like to thank you all for attending this session. I hope it was very useful to everyone, and definitely we learned a lot from our speakers. Thank you very much for your attendance, and let's go. Thank you.